Alrighty, welcome back everybody. We are now going to move into module number 4. And in module number 4, we're going to be talking about the Open Shortest Path First protocol. OSPF is an open standard protocol. It's considered an IGP routing protocol, meaning it's going to be a routing protocol that we are going to run inside of our enterprise. And it is fundamentally a link state routing protocol, which means all of the routers in OSPF are going to share information about the state of their connected interfaces and the state of their links, and that information is going to be compartmentalized and accumulated into something called a link state database. And then the routing protocol will use the shortest path first algorithm, or Dijkstra's algorithm, to analyze that database and decide which entries are going to be extrapolated from that database and put into our global routing information base. Now, before we get into the protocol itself and start to talk about some of the details of this routing protocol, let me give you a little bit of background about OSPF. It was developed in 1989. So it's over 30 years old, and there are many different RFCs that define the routing protocol itself, starting with RFC 1131, moving over to 1247, and fundamentally finding its way to 2328 for OSPF v2, and then 5709 and 6549 and 6845 for OSPF v3, both for OSPF v3 for IPv6 and OSPF v3 for address family mode. Now, in 1999 is when they actually developed the OSPF for IPv6 communication protocol, and that was RFC 2740, 5340, 6845, 6860, 7503, and then finally 8362. So what OSPF does fundamentally is it gathers all of its link state information from available routers, and it creates an entire topology or topological map of the network. That topology that we create is presented as a routing table in our OSPF domain, and provides us the ability to find the optimal paths throughout the enterprise. Now, we are going to spend some time in this section discussing not only the routing protocol messages that are going to be used with this particular protocol. We're going to talk about the algorithm that's going to be utilized with this particular protocol. We'll talk about the link state information. We're also going to spend a lot of time focusing on the neighbor discovery process. How do we exchange link state routing information? How do we calculate the best path within OSPF? And how do we perform convergence? Like I mentioned, OSPF is fundamentally a link state routing protocol, and it uses different message types to communicate, and we'll go through those different message types as well. If you recall, in our EIGRP section, we discussed different message types like a hello packet, a update, a query, a reply, an acknowledgement, and so on. In the context of OSPF, we have several different OSPF message types as well, starting with things like a hello packet, database descriptor packet, a link state request, a link state update, and link state acknowledgements. So before we get into the actual configuration and implementation of OSPF, oops, hold on one second. Sorry about that. Let's go ahead and get into some of the basics of the protocol itself first. And we'll get into the details. We're going to take a look at these different packet types. We're going to look at the format of these different packet types, and of course get into the details of why each of these packet types are necessary in order for us to facilitate adequate communication with the protocol itself. As these paragraphs describe, it is a link state routing protocol. Like I said, we have those 5 different message types that are used to advertise information within OSPF, but ultimately we're sharing network layer reachability information using link state advertisements, which then go into our link state database, and ultimately the routers within the autonomous system are going to synchronize their link state databases with the other routers in the topology. One of the things that we need to be concerned with, well, at least be aware of, is how we're going to design this OSPF architecture. Unlike EIGRP, which operates in a flat environment, OSPF requires a hierarchical design with very specific limitations on how routers can be deployed within the OSPF domain. OSPF is obviously going to be an IGP routing protocol. We mentioned that previously. It's mostly used in large enterprise networks, particularly networks that require an open standard type of protocol that works across multiple vendor platforms. A similar protocol to OSPF is intermediate system to intermediate system, which is an LSR-based protocol, but that's most commonly used in large service provider core networks for core IGP routing. So if you learn about MPLS and service provider network or routing, you're going to most likely take a look at what ISIS provides. Again, OSPF was originally designed in the 80s. Version 2, which is the latest RFC, is 2328, and updates to include IPv6 in RFC 5340, which came out in 2008. OSPF is a classless routing protocol. That means that it supports subnetting, variable link subnet masking, classless interdomain routing, which by definition is those other two things, as well as summarization on certain types of devices within the topology. Okay, so in this section, we are going to talk about several different things as we go through this module. We're going to talk about the differences between OSPF v2 and OSPF v3. We're going to talk about the basic operational steps that allow our link state protocols to share information, form adjacencies, and share information. We're going to talk about different areas and router types in OSPF. We'll talk about the different design limitations of OSPF. We'll take a look at different OSPF message types, the differences between OSPF v2 and v3. What are the neighbor states, right? Down, init, two-way, xstart, exchange, loading, and full. What are the different network types, right? We have different types of networks like broadcast, non-broadcast, multi-access, loopback, point-to-point, point-to-multipoint, point-to-multipoint, non-broadcast, and so on. So we'll get into that. We're going to talk about different link state advertisement types. What are type 1 LSAs, type 2 LSAs, type 3, type 4, type 5 as an example, type 7. We'll even talk about 8 and 9 as well when we get into our IPv6 discussion. We're also going to talk about how OSPF LSAs are also flooded during on a periodic interval of 30 minutes. This is called the paranoid update. We'll talk about why that's necessary and why OSPF designers decided to incorporate that in the design. We'll take a look at the how routers exchange information in the network if we don't have a designated router. And then we'll talk about what the role of a designated router is in our topology and how that designated router changes how we share information between OSPF peers. When does the shortest path first algorithm occur? How do we calculate costs for intra-area routes as well as the cost for inter-area routes in OSPF? You're going to see as we get into this, and I talk about this a lot of in my CCIE Enterprise Mentorship Program, is that OSPF is really kind of a different type of routing protocol than EIGRP. In OSPF, yes, we are concerned about being able to reach particular destination prefixes within our enterprise, but OSPF, from a database perspective, is more concerned about routing to nodes than it is about routing to networks. So the visibility, the understanding of where those nodes exist, how those nodes are implemented in the topology, play a pretty important role in OSPF. How do I decide if I'm going to select between an intra-area route and an inter-area route, right? What is the order of operations if I'm learning about the same route from two different types of areas? And then finally, we're going to take a look at how we implement OSPF v3 in a dual stack environment, including both IPv4 and IPv6. So let's go ahead and continue on. Like I said, OSPF was developed by the Internet Engineering Task Force, and primarily they wanted to develop a protocol that addressed a lot of the limitations that we saw with distance vector routing protocols. If you recall from our previous discussions, distance vector routing protocols tend to be less aware of what the network topology looks like. They do what we call routing by rumor, because when I share routing information with my peers in a distance vector environment, I'm pretty much only sharing the routes that I've decided to use. I am not sharing the routes, all of the paths or all of the routes that I'm aware of. And so OSPF was primarily designed to address some of those limitations. It is also not a proprietary protocol, and traditionally IGRP and EIGRP were proprietary. And like I said before, version 1 of OSPF was described in RFC 1131, and the current version is 2328, OSPF v3. And it can be a little bit confusing. We'll talk about this a little bit later on. Kind of two different types of OSPF v3 that we see. But the traditional classic OSPF v3, which is used for IPv6, was specified in RFC 5340. OSPF scales to a much larger environment than traditional IGP routing protocols, certainly larger than RIP. And while EIGRP does scale to a fairly large environment, up to 100 routers in diameter, OSPF can scale pretty much indefinitely. There are some limitations to the number of routers that you can have within a particular area, and there are certainly design limitations on how areas can be interconnected, but overall, with a spine and leaf design topology that we get with OSPF, you have a lot of flexibility in how you can scale OSPF, especially if you're utilizing a lot of the enhanced features of OSPF, which make OSPF much more efficient. And we'll certainly get into all of that a little bit later on. Okay, some of the key features. It is a link state routing protocol. We've already talked about in previous lessons the fundamental difference between distance vector and link state. Just know, well, there's kind of a basic analogy that most people seem to understand fairly well. Distance vector routing protocols would be like if you're driving down the highway and you see a road sign that says Burbank, California, right? And it says Burbank 50 miles. So you have a general idea that you're going in the right direction because the sign is indicating that that city exists, and you have a general idea of what the distance is. So direction would be the vector and distance would be the miles in this particular case, but you really don't have any visibility as to what that path entails, what's included in that path. What routers am I going to touch in that path, or what exits am I going to touch in that path if we follow the roadmap analogy. Whereas OSPF as a link state routing protocol, we comprise or compile a database of all of the path information, and then we can make our own informed decision as to how we're going to reach a particular destination. So OSPF as a link state routing protocol is going to tend to have a lot more information than a traditional distance vector routing protocol. And there are some other efficiencies built into OSPF as well that make it a very, very efficient and highly scalable routing protocol. Scalability and fast convergence are always concerns when you're dealing with these routing protocols. Inherently, some of these protocols have those two features built into them, but those features can be enhanced by implementing the protocol in a much more efficient manner. Implementing appropriate scoping of LSAs in the environment by implementing summarization boundaries in the topology. Limiting the size of databases, which means reconvergence times are much faster, and so on. We'll talk about those mechanisms as we progress through this lesson. All right. OSPF has an independent transport, and we'll break down some of this in detail in a little bit in the following section, but OSPF operates purely on IP, specifically Protocol 89. There is no TCP function, there is no UDP function. Much like EIGRP, which is operating at Protocol 88, OSPF has very little overhead when it comes to processing transactions, because it sits right on top of the internet layer or the network layer, right? Depending on which model you're talking about. So we don't rely on TCP or UDP, but that does mean that we have to have mechanisms built into OSPF to ensure delivery of important messages and to acknowledge those deliveries, and we'll see that in the form of OSPF message types. We do support variable length subnet masking, And we can do route summarization. And we'll talk about how route summarization takes place. And then lastly, we'll talk about authentication. So let's kind of break down some of these bullet points here. Some of these we've already talked about. Like I said, OSPF is completely independent of any other transport layer protocol because it uses IP protocol number 89. We do not rely on TCP or UDP. Now, that is beneficial in the fact that we don't have the overhead. Certainly UDP would not really offer us any additional benefit to the protocol. IP is already connectionless, and TCP would provide perhaps too much overhead, particularly when we want a protocol to be able to converge and react quickly to changes in the topology. We know that BGP runs on top of TCP and RIP runs on top of UDP, but as a routing protocol, OSPF takes advantage of running over top of IP. Now that does pose some, maybe concern or consideration, right? Because IP is inherently connectionless. There's no guaranteed delivery. There's no order delivery of packets. And so there are some considerations that we have to have within the design of OSPF to make sure that we can handle those features. All right, very efficient use of updates. OSPF does incremental updates primarily. That means that as a routing protocol, it's only going to send updates when they are necessary and only to the neighbors that need that information. In addition, we will only send the changes. All right. Now, there is one exception, and that exception is what we refer to as the paranoid update. We'll talk about that a little bit later on, where the LSA aging timer expires, which is a 30-minute timer, and we will flood out our linked state database to resynchronize to the rest of the domain just to make sure that we have appropriate synchronization of our linked state databases. Unlike EIGRP, the metric in OSPF is very, very basic. And there are some tuning things that we need to do with the metric within OSPF, particularly with modern networks today. But unlike EIGRP with all the K values and different components of the metric like bandwidth and delay and reliability and load, the OSPF metric is based on cumulative path cost in terms of bandwidth. And we'll get into the calculation of the metric and how we can manipulate that metric a little bit later on, right? That interface cost is inversely proportional to the bandwidth. So the formula that we're going to use is 10 to the power of 8 divided by the link bandwidth in bits per second, not like EIGRP where we're using 10 to the power of 7 divided by the interface bandwidth in kilobits per second. And unlike EIGRP, the metric for OSPF bandwidth calculations are cumulative, meaning that we are going to utilize all of the bandwidths across the circuit path to identify the overall path cost of that link. And we'll get into that in detail as we start to dive into our protocol a little bit later on. OSPF uses multicast and unicast. It is not a broadcast-based protocol. Only IGRP and RIP were broadcast-based routing protocols. Generally, we try to avoid broadcasting in most modern networks as best as possible. In OSPF, we use the multicast address of 224.0.0.5. That is all OSPF routers. And we use 224.0.0.6 for designated routers, right? And we'll get into the concept of designated routers a little bit later on. The corresponding addresses in IPv6, FF02:5, and subsequently FF02:6, which represents the DR routers and BDR routers, by the way, in IPv6. As I mentioned, we do support variable link subnet masking. It is a classless routing protocol. It doesn't even do classful summarization by default. And there really is no way to turn on that quote-unquote feature like we have with EIGRP. But that's probably not something we would want to implement anyway. We can do summarization. And again, there is no automatic summarization with OSPF. We have to manually configure our summary boundaries. And unlike EIGRP, where I can configure summaries at any point in the topology, in OSPF, I can only implement it on ABRs and ASBRs. So there's a big limitation there as well. That means that your design and how you implement your areas and where you put your contiguous address space is very, very specific in OSPF. Otherwise, you will not gain the benefit of having effective summarization in your network. And then finally, authentication. We talked about authentication with the EIGRP. In OSPF, we support plain text authentication. Clearly, we're not going to use that. We support classic MD5 hash-based message authentication that uses a secret sauce or a secret key as part of the hashing process to authenticate peers. Or we can use the cryptographic SHA or secure hashing algorithm authentication. OSPF v3, because it's IPv6 based, can also incorporate both authentication headers and ESP headers for encryption through the use of the extension headers for IPsec within IPv6. And we'll actually take a look at that as part of our lesson and part of the discussions that we're going to have in this particular module. All right. So now let's take a look at OSPF operations. When we started to talk about routing protocols in general, and we started to identify how we were going to understand these routing protocols, whether it's RIP or OSPF or EIGRP or BGP, whatever protocol it is, I mentioned to you guys in previous lessons, there are basically three things that you need to be concerned with when it comes to becoming an expert in these protocols. And the first thing that you have to be familiar with is fundamentally, what are the routing protocol messages that are used by the protocol itself, right? EIGRP, like I said, uses hello packets, updates, queries, replies, stuck in active queries, stuck in active replies, and so on. In BGP, we'll use notification messages, we'll use BGP open messages, we'll use BGP updates, and so on to pass information between BGP speakers. And in OSPF, we also have different message types, and we'll get into those message types in detail. Hello, DBD, link state request, link state acknowledgement, and link state update. But that's the first thing that we're going to need to do a deep dive into and to really understand the protocol itself. The second thing is the algorithm that the protocol is going to use, right? In RIP, we use the Bellman-Ford algorithm. In EIGRP, we use the dual or the diffuse update algorithm. In BGP, we use a path vector selection process known as the path vector algorithm or BGP path selection process. And in OSPF, we use the shortest path first algorithm, which was developed in the 60s by a gentleman named Edsger Dijkstra for computing or calculating trees for defining the shortest path to reach a particular destination. Well, in his context, it was more related to mathematical concepts, but it's been adapted to OSPF. So the algorithm is extremely important. And in EIGRP, we learned about things like successor, feasible distance, feasibility condition, route calculations, metric calculations, and so on, and variance and load balancing and all those things. Those are all components of the algorithm, right? In OSPF, we're going to learn about the adjacency formation process. We're going to learn about how routes go into the database, how a router decides based on path cost, what routes to utilize, what routes to not utilize, and so on. And so that algorithm is extremely important. That's number two. And then finally, number three is to understand the data structures that are used by the protocol. Not only how do we input data into those data structures, how do we look at those data structures, analyze those data structures, and make decisions on what's happening with the implementation based on viewing and analyzing those data structures. And in OSPF, we have our adjacency table, we have our link state database, and then finally, overall, we have our global routing information base, or our global RIB. So OSPF can be pretty much divided into different steps, right? The first step would be to establish a formal adjacency with other OSPF speaking neighbors. And in order for us to form that adjacency, we're going to send out hello packets. Certain parameters of those hello packets have to meet certain conditions in order for us to form an adjacency. And then finally, we're going to use other message types to actually share information between the routers. So that would be kind of the second step, right? Share all the information in the form of link state advertisements or link state updates, and compile that information into our link state database. And then finally, run the algorithm against that database, run shortest path first, and determine what's going to be extracted from that database, not only based on what's best for OSPF, but also what's best for the global routing table, right? We still have to consider things like administrative distance and how that's going to affect how routes get inserted into the routing table. But then ultimately we put that information in the routing table and we are able to route to our particular destinations. All right. So like I said, the second step in the process is to go ahead and exchange link state information. That's going to allow us to get that picture of the topology. Those link state advertisements allow us to share that information, and that will go into the link state database. And I promise we are going to spend a lot of time analyzing that database and identifying the importance of that database and how it works in our overall OSPF implementation. Finally, like I said, once we're all synchronized, we all have identical LSDBs, we can start to do our best path calculation, and then those routes would become candidates for the global routing table. And again, the best path calculation, well, in OSPF, it's relatively basic. All right, so the next thing we're going to take a look at is the hierarchical structure of OSPF. This is a really, really important concept. OSPF, like I said, is a hierarchical routing protocol. It can be implemented as a flat routing protocol. You can implement OSPF in a single area configuration, and typically you would make that area 0. Because at a later date, you may decide to add additional areas, and you always have to have an area 0, which is considered your backbone area in order to facilitate multi-area OSPF use or configuration. So as a hierarchical routing protocol, there are some guidelines as to how these OSPF autonomous systems are designed. Now, ultimately, we will spend some time in the next section, actually 4.5, talking about what those guidelines are and why they're important. But let's take a look at what we see on this slide here. So overall, the entire OSPF domain is called an OSPF autonomous system, okay? And that is essentially all routers that are part of the same OSPF domain that are sharing and synchronizing their link state database. We have in a multi-area design a two-tiered architecture. We have the spine, which is your backbone, and we have your leaf areas, which are your non-backbone areas. So this is a leaf area, that's a leaf area. So it's a spine and leaf architecture. All right, and a router that has all of its interfaces in the backbone, this is considered a backbone router. Makes sense, right? All the interfaces are in the backbone. Now, area 0 is typically defined as the backbone within OSPF, and there's some limitations as to what types of routers you can have in the backbone and how many you can have, but overall, it's still just a routing domain. It's still just a routing area. Now, the backbone area cannot be a special area type. We'll talk about special area types a little bit later on. Stub area, totally stubby area, not so stubby area, totally not so stubby area, and so on. We'll talk about that later. And also keep in mind that the backbone typically wouldn't have clients or servers or network devices in it, although it could function as a regular routing domain. But generally speaking, the backbone is there to interconnect all of our other areas. Okay? Speaking of interconnecting areas, we have area border routers. This guy here and this guy here. Any router that has an interface in the backbone and a non-backbone area will be considered an ABR, an area border router. These routers play a very, very pivotal role in OSPF. Not only do they allow connectivity to other areas and attach those other areas to the backbone, but these are the routers that allow us to limit the scope of LSA flooding throughout our autonomous system by implementing things like summarization and also by rule, right? By rule, certain LSA types are simply not allowed to leave a particular area. So these routers play a very specific role in our OSPF design, and we'll see that as we go through our discussion. All right. By the way, an ABR, you're not limited to one ABR. You can have multiple ABRs to interconnect the backbone to an area. And by the way, an ABR can also be a member of multiple areas. So I could say, for example, extend area 2 over to that ABR for redundancy, for enhanced routing functions, whatever I might want to do. But there are some other limitations that we'll talk about in the next section. So area border routers, not really anything particularly special that we configure on those routers to make them ABRs. It's simply the fact that we're placing certain interfaces into different areas makes those routers ABRs. But there are some considerations on what we can do on those ABRs and how those ABRs can be utilized in our OSPF domain. Another special type of router is something called an autonomous system boundary router. Now, in all the books and all the materials that we see, we typically see an ASBR attached to the backbone. However, ASBRs don't only have to be attached to the backbone. They can be attached to non-backbone areas as well. What is an ASBR? An ASBR is any router in OSPF that takes routes from an external routing process, BGP, EIGRP, another OSPF process, RIP, even static or connected routes that are redistributed into OSPF. All right, we see that quite often in a lot of enterprise designs. We're trying to inject routes from other routing domains and so on. All right, now that ASBR can only be connected to certain area types. It cannot be connected to a stub area, and it cannot be connected to a totally stubby area. But it could be connected to the backbone. It could be connected to normal areas. It could be connected to an NSSA, a not so stubby area, or a totally NSSA. Totally NSSA is something we'll talk about a little bit later on as well. Okay, any router that redistributes any type of route into OSPF would automatically become an ASBR, and those routers are going to generate certain types of LSAs. We can do summarization on those routers as well for those external networks and so on. Finally, we have our normal routers, or what we call internal routers. Internal routers are routers that have all of their interfaces in a non-backbone area. And keep in mind what I'm saying there. Interfaces go into an area, not routers. Unlike EIGRP, where we put a router into an autonomous system, in OSPF, we put router interfaces into an area. And by definition, how those interfaces are configured will determine what type of router it is. So we kind of broke down all of this information here. And again, we'll get into a lot of the design limitations and some of the considerations with OSPF as we continue on through our lesson. All right. In fact, that's the next thing we're going to talk about. So I just want to highlight that we discussed each of these. We talked about what an ABR is. We talked about what an ASBR is. We talked about what an internal router is. And we talked about what a backbone router is. Okay? So what are some of those design limitations that we need to consider? Number one, and there are a few, we're going to talk about the basic design limitations. Certainly when it comes to implementing an advanced OSPF implementation, there are some other things to consider. But let's talk about some of the basic ones, right? Number one, and there are exceptions to these rules, by the way. We'll talk about what those exceptions are. But as a rule of design, these rules should always be followed. Exceptions should only be temporary and only represent temporary states as you're kind of modifying your OSPF design or incorporating new external networks in the design and so on. So as a design principle, these are the rules that we're going to follow. Number one, one area zero. And that area zero has to be contiguous, meaning that we can't have area zero here and then have area zero down here as well. Now, like I said, there is a way to facilitate this by creating something called a virtual link between the ABRs that connect those two areas, but that's only as a stopgap measure until you can implement the design correctly. Because there are some limitations when you're running virtual links in an OSPF domain. So number one, the backbone has to be contiguous. It can contain many, many different routers. and it can be connected to lots and lots of different areas, but it has to be contiguous. Number two, all of the non-backbone areas, in this example, Area 1, Area 2, and Area 3, have to have at least one direct connection to the backbone. All right, now that doesn't mean you can't have more than one. Like I said, you can have multiple ABRs if you want to put in another ABR here and have different connections going into that domain or that area for redundancy. Or you could, like I said, extend an ABR to allow connectivity to another area. So an ABR can be a member of two different areas. It's kind of hard to draw that here. So Area 2 is limited to these two routers, and Area 1 encompasses these three routers. So you are allowed to do that. Another thing that you can never do is you can never connect areas or routers together in different areas. One of the parameters in order for OSPF routers to establish an adjacency is that the area ID that the interface is in has to match with your peer. And in this particular case, that interface would be in Area 2, and that interface would be in Area 3. So there's no way that those two interfaces would be able to, those two routers would be able to form a peering relationship over that link. All right? Area ID is one of those things that's advertised as a parameter in our hello packet. Now, there are some other limitations. For example, how many entries can you have in a database within an area? How many particular nodes can you have in an area? And certainly some more advanced design considerations. But we're focusing primarily on our basic architectural restrictions in this particular case. All right. So what we're going to do now is talk about basically, and we'll see this in more detail as we get into the discoveries, and we'll actually do some Wireshark captures and take a look at these. But what are the message types? One of the things that we're going to take a look at when we go into our discoveries, we have Discovery 6 coming up where we're going to do our basic implementation. But one of the things that we talk about is what is the packet format for an OSPF message? Rather than talk about it in detail here, I'll wait to take a look at it in an actual Wireshark capture. But we have essentially different types of packet formats, right? We have an OSPF v2 packet format, and we have an OSPF v3 packet format. And that's going to include a version field, a type field, packet length, things like, whatever's in the OSPF header, right? And in IPv4, the OSPF header is 24 bytes, and in IPv6, OSPF v3, that header is 16 bytes. And then we have our variable length field, which is our data. Now, that data is what is going to include the messages themselves. Unlike other routing protocols, particularly BGP and RIP, OSPF does not carry data using a transport layer protocol. It uses IP datagrams using protocol number 89 to carry those messages. And we define 5 different message types for different types of OSPF communication. OSPF uses hello packets to discover neighbors and build adjacencies between those neighbors. And I would also add maintain those adjacencies. We use database description packets or database descriptor packets for database synchronization. We'll talk about how that is applied when we go through the process of how OSPF routers form adjacencies. And then we have link state requests, which allow us to essentially identify or request information. This is typically done in the loading state. The DBDs are going to be done in the XStart and exchange state. We have a link state update, which is typically either a unsolicited update based on changes in the topology or a response to a link state request. And then we have a link state acknowledgement. Now, out of all of these different packet types, only 3 of these packet types are actually acknowledged: the database descriptor, the link state request, and the link state update. It wouldn't make sense to acknowledge an acknowledgement, and hello packets are sent periodically, so there's really no reason to acknowledge those. Okay, so how do we define these different message types? Let's start by talking about the hello packet in detail, right? Hello packets are used to form kind of an advertisement, if you will, or a greeting to allow me to advertise myself as an OSPF router to other potentially adjacent routers within my broadcast domain, and to also accept information from other adjacent routers in my broadcast domain. And the purpose of the hello packet is to establish that adjacency or that relationship between those neighboring devices. It also identifies key parameters of the communication process, right? What is the router ID of the message or of the peer? What are the specific timers, hello and dead intervals for that peer? If I'm running authentication, that would be defined in the hello packet as well. DR, BDR information, even neighbor information would be seen in the hello packet as well. So we use these hello packets to establish and maintain these adjacencies. And again, we'll see this when we go through the discovery. I will open up a Wireshark capture. We'll take a look at a hello packet in detail. We'll look at what the packet header looks like, and we'll take a look as well as what the hello payload looks like. The database descriptor packet or database description message contains descriptions of the topology in the autonomous system, right? It's not the entire contents of the link state database, but it allows us to convey information about the link state database. Communicating the entire link state database could take lots of different messages. Those databases can get really, really large. So instead, we're going to use these database description packets or database descriptor packets to provide a summary description of the link state database itself. And we'll see how this process is managed in the adjacency process that we talk about over the next few sections here. Link state request, as the name implies, I'm requesting link state information. Now, typically this would only happen during the synchronization process. When OSPF routers form an adjacency, they go from the down state to the init state, to the xstart state, to the exchange state, to the loading state, and finally to the full state. And in each one of those states, certain things happen during this adjacency process. One of the critical elements is to exchange routing information. So once I've gone through the xstart state, and I've gone through the exchange state where I've exchanged my database descriptors, I now need to make sure that I'm synchronized with my peer. So I'm going to send out a link state request to request information that my peer might have that I don't have. And again, we'll see the link state update. It's going to have the 24-byte or 16-byte header, depending if it's IPv4 or IPv6. And it's going to have LSAs, LSA numbers, which is a 4-byte field, and then it'll have a list of all the LSAs. And again, we'll take a look at that in Wireshark a little bit later on. A link state update are messages that contain update information about certain links in the link state database. They're either sent in response to a link state request message, but they can also be sent out in the initial synchronization process, right? Or when a topology change occurs, right? I'm going to send an update if a link goes down or if a new link comes up and so on. Lastly, we have the link state acknowledgement, and the link state acknowledgement message is what provides reliability with OSPF in the exchange of those three packet types: the database descriptor, the link state request, and the link state acknowledgement. All right. Now we are going to talk about different LSA types: router LSAs, network LSAs, summary LSAs, ASB summary, or network LSAs, excuse me, summary LSAs, ASBR summary LSAs, those are my type 4s, AS external LSAs, which are my type 5s. We probably won't spend too much time talking about type 6s, those are used for multicast, but we'll definitely talk about NSSA external link state advertisements, type 7. We'll talk about link LSAs, which is for OSPF v3. Those are type 8s, and we'll talk about intra-area prefix LSAs as well, which are type 9s. 10 and 11 we don't really talk about either because those are opaque. They're used for future use. But in any event, we got a whole section later on where we talk about all of the LSA types, and we get to spend a lot of time learning that. So our final topic here before we get into our first discovery is, what is the difference between OSPF v2 and v3? Now, keep in mind there are actually three different types of OSPF. Traditional OSPF for IPv4, which is essentially kind of the original version of OSPF. If you recall, That was the version of OSPF that was introduced in 1989 with 2328. We have traditional or classic mode OSPF v3 for IPv6, which was developed in 1999. And I'm not sure, I think it's 5340 was the primary RFC, but I know that they have 6845 and 6860 and 8362. But in any event, it's the 5340 is the primary RFC, and that was developed in or released in 2008 to describe OSPF for IPv6. But then we have this third option here, which is also incidentally called OSPF v3. Huh? Right, OSPF v3. So you need to make a distinction if you're discussing OSPF v3. Is it classic OSPF v3 or is it address family OSPF v3? Much like we talked about with EIGRP, we can run classic mode EIGRP or we can run address family mode EIGRP or named EIGRP. Now, it's not quite the same in OSPF. And the primary reason for implementing named EIGRP was wide metrics and picosecond delays and more granularity in the metrics, as well as a combined configuration space for EIGRP. In OSPF, it's completely different. I'm not going to spoil the surprise. We'll talk about that in one of our final lessons in this module when we talk about OSPF v3 address family mode. You can also see here how we implement this, right? We go into global configuration mode, router OSPF, and then we put in the locally significant process ID for OSPF. In IPv6, IPv6 router OSPF, and we put in the locally significant process ID for that. And obviously we're going to do peering over IPv6. We're going to use IPv6 as our primary transport. New style OSPF, OSPF v3AF, we use router OSPF v3, and then we specify a locally significant process ID. And by the way, we're transporting, even though it is combining both IPv4 and IPv6 functionality, we're actually using IPv6 as our transport. So we don't have separate transports. Unlike EIGRP named mode, if you're running v6 and v4, you're still maintaining separate layer 3 transports for EIGRP. But in the case of OSPF, we use a single transport to transport all of that information. Again, we'll spend a lot of time going in into all these concepts a little bit later on. All right. 15.1.3s was when Cisco released OSPF v3 address family. And again, we'll spend some time talking about how that works a little bit later on. All right. So let's take a moment to go into our first discovery and take a look at some of these concepts and some of these theoretical pieces in detail within our discovery. All right, in this discovery number 6, we're going to be configuring OSPF v3 for IPv4 and IPv6. So in this discovery, we're going to basically learn how to configure and establish our OSPF v3 configurations using address families. This is something, by the way, that we did in the Encore class, but we're going to do it again because it is a discovery and we want to make sure that we feel pretty comfortable with what's going on with these configurations. We're going to take a look at what the impact of the hello and dead timer parameters are on the neighbor adjacencies. We know that, in fact, if those timers don't match, that's going to be a problem, right? We're not going to be able to form an adjacency. We're going to talk about the roles of the DR and BDR, something that we also talked about quite significantly in the Encore class, right? How do we control the DR-BDR election using priority or using the router IDs? We're also going to set up a passive interface where the OSPF adjacencies need to be established, and that would actually would not be established, I should say, because if we did do passive interface on interfaces where neighbors should exist, then that's going to break the protocol, right? We'll also have access to 5 different routers here, R1 through R5. R1, R4, and R5 are already pre-configured with OSPF v3. R2 is currently running OSPF v2 and traditional OSPF v3, in other words, classic configuration. We're going to be responsible for migrating the configuration of R2 to OSPF v3 address families and fully converge between the new a new branch router R3 with OSPF v3, that should say OSPF v3 address families as well. All right, so we're going to start by looking at the OSPF configuration on router 2. We're going to migrate router 2's configuration to address family mode. We're going to configure OSPF v3 on R3, address family OSPF v3 on R3. Take a look at the v3 configuration on R1. Take a look at the DR-BDR election, and then we're also going to be tuning the OSPF v3 timers as part of the process here as well. This is our topology that we can see here. The DR-BDR election on router 4, DR-BDR election. This is a multi-access network, so there is going to be a DR-BDR election on this network. There actually technically would be one on this WAN link as well because it is Ethernet, but we don't really care about it too much because there's only 2 routers, which means that it doesn't matter who the DR or the BDR is, we still have to have a full adjacency with all the routers on the segment. All right, this is our topology, same as what you have in GNS3, with the exception of the interfaces. Anything that starts with a 0 is going to be a 1. The serial interfaces are going to be 2, 0 on both sides. All right, this is our table describing all of our IP connectivity. So our first task is to go into router 2 and verify the OSPF configuration on router 2. So let's go ahead and do that. Router 2. All right. Well, we could do, show run section OSPF, but it depends on whether or not they're using network statements or they're explicitly enabling the protocol on the interface. You can see from the output here that for IPv6, we enable the protocol directly on the interface. That's always been the case, right? Whether it's EIGRP or OSPF, for IPv6, we don't use network statements. We enable the protocol directly on the interface. So we can see from the output that it's enabled on this interface here, which is loopback 0, serial 20, it's enabled. I can confirm that by going back to my router here. Show run interface serial 20. OSPF process ID 1. That does match the global routing process, which is really important. You want to make sure that the process that's enabled on the interface matches the global routing process that you did for classic OSPF v3. Also notice that the process ID is the same for OSPF v3 and OSPF v2. That does not actually have to be the case, because remember, we're running classic OSPF for IPv4 and IPv6, which means completely separate protocol stacks, completely separate data structures, completely separate message types, or at least message sending of messages and so on. All right. Also, my loopback show run interface loopback 0. I can see that we're running OSPF on the loopback interface as well. So it looks like OSPF is configured correctly, right? Also check your areas. 172.16.12 is in area 1. 192.168.2 is in area 1. Is that actually correct? This is on router 1, right? Router 2, excuse me. Which is correct, right? Router 2 is in area 1. So the loopback is in area 1. This 12.0 link is in area 1. And with the IPv6 configuration, it's also in area 1 and area 1 here. Okay? So it looks like the configuration is accurate in this case. Notice that OSPF v2 and traditional OSPF v3 are configured with process ID 1 for area 1. All OSPF v2 IPv4 configurations are gathered under the global routing configuration mode, while the traditional OSPF v3 is on global and on interfaces. We don't have an option with OSPF v3 to do network statements. So we kind of have this scattered configuration again where some of the configs are on the interface, some of the configuration is in the global routing process. Traditional OSPF v3 is going to carry our v6. How would I enable this? IPv6 unicast routing to enable the global IPv6 routing process. Start the OSPF v3 process by putting in the command IPv6 router OSPF and then specifying the process ID, which is already done in our router. Set the router ID. Now again, you don't technically have to set the router ID if you have some v4 interfaces, because the router ID will use the highest active IP address on a loopback, or it will use the highest active IP address on a physical interface. But if you want to control what the router ID becomes, you would set the router ID manually, and in our case, that's what's done, right? Our case, the router ID is set statically right here under the routing process. All right? All right. Passive interface default, what does that do? That makes every OSPF interface passive, which would break adjacencies. No passive interface explicitly disables the passive interface feature on whichever interface that you specify. And again, you can do that, or you can just explicitly make an interface passive. We talked about this, right? If you have more interfaces that are passive than are not, this would be the approach. If you have only a few interfaces that are passive, this would be the approach. All right, so all this text right here is just a summary of what we just discussed, and it kind of breaks down everything that we just talked about. What is the process ID? The router ID is a 32-bit number, but it does not have to be an address. In other words, it could be 0.1.0.1. That's not a valid IP address, but it could be used as a router ID. Okay? Obviously, IPv6 addresses are different from IPv4. We can have multiple IPv6 addresses on a single interface. In fact, we always do anyway, right? If you enable IPv6 on an interface, it's going to have a link local address and potentially a global unicast address, which is the address that you specify as an administrator. But you could have multiple global unicast addresses, and you could also be participating in multiple multicast groups, depending on what type of protocol is running on that particular interface. If I go into, for example, my router here, and I say show IPv6 interface serial 20, we have our link local address, which is statically configured as FE80:2. I have my global unicast address. Global means routable. Unicast means single, right? This is a single address, an individual host address. This is the actual subnet, but this is the actual host address for the interface. And then you'll notice here that I've also joined all these other multicast groups. FF02:1, for example, all multicast routers, hosts, all multicast hosts. FF02:2, all multicast routers. FF02:5, all OSPF routers. And finally, FF02:1:FF00:2, that is a duplicate address, multicast address that we can use for duplicate address detection for our interfaces. All right. So we can see that the router has joined several different multicast groups. All right. So do we have any neighbors? If I do a show IP OSPF neighbor, let's go ahead and do that on router 2. Show IP OSPF neighbor. We don't have any neighbors. Show IP OSPF, show IP route OSPF. We don't have any OSPF routes, so we're not getting anything as of yet, right? Even if I do show IP OSPF protocols, show IP OSPF protocols, show IP protocols. I don't know why I did show IP OSPF protocols. We can see that we do have OSPF configured on the interfaces. So just like we talked about when we were troubleshooting EIGRP, in this case, we're trying to verify functionality of OSPF, and it appears as though it's configured correctly on this side, so we need to, of course, check the other side. All right. Now, if we check IPv6, show IPv6 OSPF neighbor, we do see that we have an adjacency here. The neighbor ID column is the neighbor's router ID. The priority is the priority of the peer, which is a number from 0 to 255. Generally, the higher the number, the more likely it is that you're going to become a DR for a particular segment. But what is the priority of 0? Remember we talked about that? Priority of 0 indicates that you can never be elected as a DR or BDR, but look what type of interface this is. This is a serial interface. Because it's a serial interface, there is no point-to-point, I mean, it is a point-to-point serial interface. There is no DR, BDR election. So automatically the priority was set to 0. The dash here indicates that we're not doing a DR, BDR election. Otherwise, we would see either two-way there, or we would see, excuse me, not two-way, DR, BDR, or DR other. That's what would be listed in that, the right side of that, that forward slash. All right. So we do have a v6 neighbor. If I did a show IPv6 route OSPF and a show IPv6 protocols, show IPv6 route OSPF, we are getting some inter-area routes. Remember, OIA represents routes that come from another area, which would make sense in router 1's case, right? Because, I mean, router 2's case, because router 2 is in its own area. It's an internal router in area 1. And if I do a show IPv6 protocols, I can see that we're running process ID 1. These are the interfaces that are running the protocol, and this is the particular router ID. All right. Although R2 is configured using traditional OSPF v3, it has successfully established an OSPF v3 neighbor adjacency with R1 and it's learning routes. The reason why they specifically mention this is because R1 is running address family mode. So this does demonstrate that OSPF v3 classic mode is compatible with OSPF v3 family mode. Now it's a little bit curious why we're not really seeing anything with v4. I guess that was the intent of this exercise, was to not have OSPF working for IPv4 yet. I'm assuming that that's something we're going to fix on router 1 later on. All right? So our next step is to go ahead and migrate router 2 to OSPF v3 address family mode for IPv4 and IPv6. So we can have a single routing process that transports both the v4 and v6 routes. We have a single database that's going to carry our v4 and v6 information. We establish our adjacencies individually for each address family, but we verify the adjacency with a single command, show IP OSPF v3 neighbor. And then we're going to come up with our specific address family mode configurations for each of the stacks. Remember, this feature is supported on 15.1.3s and above for Cisco iOS and 15.2.1t. We're running 15.4, I believe. All right. Let me see. What are we running here? Show version 15.2.4. Yeah, so we're fine here. You make loopbacks passive just to demonstrate the concept of passive. Yeah. Obviously, a loopback interface doesn't need to be passive. You're not generating hello packets out of a loopback. The router's smart enough to know that a loopback interface doesn't go anywhere, so it's not really technically going to generate traffic on a loopback anyway, but they want you to see the passive interface command. All right? So let's go ahead, and we did this in our Encore class, right? We did have a discovery where we configured OSPF v3. And if you recall from the Encore class, we can actually configure OSPF v3 on top of the classic configuration, which allows us the ability to kind of migrate to OSPF v3 without tearing down our entire OSPF configuration. So let's go ahead and do that. Router OSPF v3.1, remember that process ID is specific to OSPF v3 address family mode. Router ID 2.2.2.2, and as he just said, let's make loopback 0 passive just so you know that that loopback interface exists. So router OSPF v3.1, router ID 2.2.2.2, passive interface loopback 0. Show run section router. You'll notice now that our configuration has changed quite a bit. If you recall previously, we had OSPF for IPv6 classic mode configured. We had an IPv6 router OSPF command. That's gone. We no longer see the IPv6 router OSPF 1. Because as soon as we enabled OSPF v3, notice what it did is it automatically configured OSPF for IPv6 under the OSPF v3 process. It left the v4 stuff, but it added the v6 stuff under the OSPF v3 process. Again, keep in mind that unlike EIGRP, where named mode still requires you to have a separate v4 and v6 config, in OSPF v3 named mode, address family mode, we're using v6 as our transport to exchange all of our information. We still have some classic OSPF v3. If you do a show run interface serial 20, you'll see that we still have the classic OSPF v3 on the interface. So we're going to have to migrate our interfaces as well to this new OSPF v3. Okay? So we just did the show run section router. We can view the result of the OSPF configuration by using the show run section router command. The old OSPF router configuration, IPv6 router OSPF, has disappeared, and it's been replaced with the address family submode. The newly entered router ID is displayed in the router configuration mode. The original router ID that was configured using traditional OSPF v3 was automatically placed under the v6 address family. Again, passive interface is passive interface. We do this per address family. And we know why we do passive interface, right? We do passive interface to suppress the protocol from running on the interface, but still, it still allows us to have that protocol or that network advertised as part of OSPF. All right? So it's a very common method for kind of filtering out the routing protocol on interfaces where you're not typically going to have a peer. We're trying to prevent a route injection attack or somebody putting a rogue OSPF router in the network, and then all of a sudden they're able to inject routes and do everything else. All right. All right. So now we're going to do a show OSPF v3 neighbor as opposed to doing show IP OSPF neighbor or show IPv6 OSPF neighbor. We're also going to do a show IPv6 route OSPF and a show OSPF v3 database. So show OSPF neighbor, and we can see we have our address family v6 neighbor, which we've established. Now, once we've migrated completely, including the v4, we still would see an address family for v4 listed under here. We don't see it right now because we haven't migrated v4. If I did a show IP OSPF neighbor, I don't see that information anymore, but I didn't have a v4 neighbor before anyway. If you recall, we checked that before and it wasn't there. If I do a show IP OSPF interface, I can see that I'm running OSPF v2 on my interfaces. I just don't have any neighbors. All right. Show IP IPv6, I think that's what we were looking at. Show IPv6 route OSPF. We can see that we're learning those prefixes, the same prefixes we had before we switched to address family mode. And then they wanted us to also look at the database, show IPv6 OSPF v3, show OSPF v3 database. Not IPv6, but because remember, again, we only have one database now. Well, we will once we complete the configuration. One database that constitutes all of the prefixes that we're learning in both stacks. Significant difference from EIGRP, where in EIGRP, we still maintained separate data structures for each protocol stack, regardless of the fact that we were running named mode or address family mode configuration. All right. So we can verify OSPF v3 operations using the old commands, show IPv6 OSPF neighbor, show IPv6 OSPF database, or the new style, show OSPF v3 neighbor, show OSPF v3 database. So you could actually go back and say, well, let me look at the v6 neighbor table, let me look at the v6 topology table, or you can actually look at the combined tables by using the OSPF v3 commands. We haven't seen any of the combined stuff yet because the v4 piece hasn't been migrated. But once the v4 piece is migrated, then we can start seeing the combined information. All right. Now, despite the change to OSPF v3, some of the configuration is still maintained. We still have OSPF v3 enabled on the interfaces, the classic OSPF v3. So what we need to do now is do our complete conversion and enable OSPF v3 address family mode on the interface. And this is where it kind of separates itself from EIGRP, because in EIGRP, everything was done under named mode. All of our interface-specific commands, everything was done under named mode. In OSPF v3 address family mode, we still have kind of some configs that go under the interface and some configs that go under the address family configuration. All right, we're going to put both of these interfaces into area 1. So let's do that. Config T, interface loopback 0, IP OSPF, OSPF v3, process ID 1, area 1. Oops, what did I miss there? IPv6. Yeah, we need to specify the stack. OSPF v3, IPv6, 1, area 1. OSPF v3, 1, IPv6. Am I in the right interface? OSPF v3, 1, IPv6, area 1. That's what I'm trying to do. IPv6, area 1. I just didn't type enough characters because it can be IPv4 or it could be IPv6, and I'm trying to tab out here and it doesn't know if I'm trying to do v4 or v6. So interface serial 20, yeah, 20, do show run interface serial 20. I just want to show you how this command will be replaced once I put the other command in. do show run interface serial 20, and we can see that the classic command was automatically replaced when I put in the OSPF v3 command. All right. The preferred interface mode command for the new style is OSPF v3 process ID, IPv4 or IPv6 area ID command. This allows us to selectively activate the OSPF v3 process for address family mode. With the OSPF v3 address family feature, you may have 2 device processes per interface, but only 1 process per address family. Okay? Which means that you're not allowed to run multiple processes within the address family, but you can still have multiple processes between different address families on the interface. All right, if we're doing IPv4 address families, we have to have an IPv4 address configured on the interface first. For IPv6, we don't have to have a global unicast address, but IPv6 does have to be enabled on the interface because there has to be at least a link local address. And the only way that there's a link local address on an interface running v6 is if v6 is enabled on the interface. All right? You don't need global unicast addresses for OSPF to work because, again, our adjacencies are formed using link local addresses. They're not formed using global unicast. Now, for throughput, for network reachability, getting all the way through the network, you would have to have global unicast addresses because link local addresses are non-routable. So I can't do a trace route through a network if my transit links in between are only running link local. That doesn't mean that I can't get end-to-end connectivity though, because we route to nodes, we don't route to networks. So it's a kind of a weird scenario where you could potentially reach a destination even though you don't have global unicast all the way through. So you could ping the final destination, but you can't do a trace route because trace route requires each node to respond to the ICMP echo requests. And a node that doesn't have global unicast can't respond. All right? And we can, of course, verify our config by doing a show run. I just did that with the section command. And we can verify that we still have our neighbor relationship by using the show OSPF v3 neighbor command. Do show OSPF v3 neighbor. And we see we have our neighbor relationship here. The configuration on router 2 shows that the new style interface mode commands have replaced the old style commands. The OSPF operation has not been affected. We still have our adjacencies, we still have our database, we still have a routing table, because again, we kind of did this in progression. We started with a classic mode configuration, we replaced the classic mode globally, and then we replaced the classic mode on the interface. But because classic mode is compatible with traditional, with the address family mode, we didn't lose connectivity during the configuration process. All right? On router 2, they want us to remove the OSPF v2 process and enable the OSPF v3 process for IPv4. Notice how we do that. Get rid of the entire global process for OSPF v2, go into OSPF v3 address family mode, go into our IPv4 address family, make our loopback passive, and then go under each of our interfaces and enable the protocol explicitly on the interface. So we're going to do no router OSPF 1. We're going to do OSPF v3, router OSPF v3, 1, address family IPv4. Now, this is slightly different than what we saw with EIGRP, right? In EIGRP, when we went into address family mode, we had to specify the autonomous system number. We're not doing that in the case of OSPF because there's only a single process ID for both address families. And we've already identified the process ID when we went into the configuration. All right, so unicast. And then we're going to make sure that loopback 0 is passive. Then we're going to go into each of the interfaces and enable the protocol directly on the interface. So passive interface loopback 0, exit, exit, interface loopback 0, OSPF v3, 1, IPv4, area 1, interface serial 20, we'll do the same command. Notice that we did get an adjacency now. All right. Let's see, nothing really here that we didn't already discuss. So let's go ahead and do our verification. Show OSPF v3 neighbor. And notice here that with one command, show OSPF v3 neighbor, we get to see both address family relationships. The v4 address family relationship and the v6 address family relationship. Could I still run the command do show IP OSPF neighbor? Nope. Could I run show IP v6 OSPF neighbor? Yes. So it's kind of weird, right? One shows you the v4 relationship, one doesn't. And this is, again, what's different between EIGRP and OSPF. In EIGRP, we would have essentially separate data structures for v4 and v6. When we're configuring OSPF v3, the adjacency is only formed over v6. Even though it does say that we have a v4 neighbor, technically that adjacency is really only formed over v6. Because v6 is our transport. There's no reason to form an official adjacency over v4 because I'm not exchanging any information through v4. I'm exchanging all of my information through v6. I mean, if I did a Wireshark capture on that link, you would expect, if this was EIGRP, you would expect to see hello packets for both stacks, right? You'd expect to see v4 hello packets, and you would expect to see v6 hello packets. In this case, if I do the Wireshark capture on the serial link, that will not be the case. Okay, now specifically we're looking at, in this case, router 2222. Which is going to be FE80:2 right here. Oops, did I click on the wrong one? Nope, that's the right one. All right, so this is my hello packet. And again, it tells me I'm running address family mode, IPv4 address family mode. But it still has all the same information I would expect a hello packet to have. What's my timers? Who's my active neighbor? Which means we've gone beyond the two-way state in this case, or at least gone up to the two-way state, and so on. But you notice what we're not seeing here. I'm not seeing any, I'm not filtering anything, and I just did a capture on the wire. I'm not seeing any v4 traffic at all. Everything is carried over v6. What's the moral of the story here? The moral of the story is, and if you're going to run OSPF v3 address family mode, you have to have IPv6, don't you? Because that's how we establish the adjacencies, that's how we transport the information. We don't have a choice, we have to run v6. Of course, there wouldn't really be any reason to switch to OSPF v3 address family mode if you weren't running v6 and v4, because you don't gain anything from that configuration. All right. Show IP route OSPF v3 would show our v4 routing table. Show IPv6 route OSPF v3 would show our v6 routing table. So do show IP route OSPF v3. We're getting our three internal routes, intra-area routes, I should say. Do show IPv6 route OSPF v3. Guess it doesn't let us do that filter for OSPF v3 for IPv6. But we can still see the routes. If we just did OSPF, we can still see the routes here. And we know that we've converted completely to address family mode configuration. We can monitor the v4 routing table that is computed from the OSPF v3 database by using the show IP route OSPF v3 command. The OSPF v3 keyword filters the content of the routing table and displays only the OSPF v3 routes. If I did a show IP route OSPF, I would not see anything. Again, because we're now operating fully in address family mode. All right. Now, what about the database? We did spend quite a bit of time in the Encore class talking about how to analyze the OSPF database. This command show us OSPF v3 database inter-area prefix. What type of LSAs am I trying to monitor in this particular case? Inter-area prefix LSAs. I'll give you a hint. 3. Type 3. Right. That was the hint, was the answer, actually. These are summary LSAs, right? Inter-area prefix LSAs are summary LSAs, right? They're just renamed. Normally, they would just be called summary LSAs, but they renamed them to inter-area prefix LSAs. Remember, this is an IPv6 concept when we renamed our type 3s to inter-area prefix LSAs, but it does represent essentially the LSAs that are coming from another area. But notice we're using one command to see both the v4 and the v6 inter-area prefix LSAs. The reason why it's a little confusing is because in traditional OSPF, they weren't called inter-area prefix LSAs, they were called summary LSAs. So let's run the command show OSPF v3 database inter-area prefix. Show OSPF v3 database inter-area prefix. And what we're looking at here, remember this is on router 2. So 13 is this network over here. That's definitely an inter-area prefix, right? It's coming from area 2. And we're seeing the 4.0 subnet, the 145 subnet. Those are definitely inter-area prefix, right? You look at the topology, 145 is coming from area 0. The 4.0 loopback is coming from area 0. All right. The IPv6 inter-area prefixes, this again is the one in area 2. This is in area 0. And this is the loopback on router 4. If I just did show OSPF v3 database, you would see the summary of the database. And here again are those inter-area prefix link states. These are the v4 ones, right? And if we keep going, these are the v6 ones down here. That corresponds to what we would expect to see in our topology. Because remember, the inter-area prefix LSAs are the LSAs coming from other areas. Those are my type 3 LSAs. Make sense? All right. A router maintains a single OSPF v3 database, which includes different LSAs, type 1, type 2, type 3, type 4, type 5, type 7, etc., type 8, type 9 if you're running IPv6, and so on. Now they want us to go ahead and configure OSPF v3 for IPv4 and IPv6 on router 3. We're going to enable unicast routing, OSPF v3.1. We're going to set a router ID of 3.3.3.3, make loopback 0 passive, go into v6 unicast, set the router ID, make loopback passive, and then we're just going to go into our interfaces and put them into area 2. Keep in mind on the Ethernet side, it's Ethernet 1.0 in our particular case. All right, so let's go into router 3. IPv6 unicast routing. Router OSPF v3. Process ID 1. Address family IPv4 unicast. Passive interface loopback 0. Router ID, did they say 3.3.3.3? Yes. Okay. 3.3.3.3. Address family IPv6 unicast. Passive interface loopback 0. Router ID 3.3.3.3. Exit, exit. Interface loopback 0, IPv6 OSPF v3, sorry, just OSPF v3, 1 IPv6 area 2, and also IPv4. Remember, we have to still enable it per protocol, and then we want to do Ethernet 1.0, same thing. And that's it. All right. All right, so we've gone through, we've implemented OSPF on our router 3. Make sure that my recording is going here. Yep, it is, okay. So we've implemented OSPF on router 3, OSPF v3. And obviously, before we're going to run OSPF v3, we are going to have to enable IPv6 unicast routing. That's our protocol stack that we have to enable on the router. Once OSPF v3 is enabled on Ethernet 1.0 of R3, we establish adjacencies with R1. So we can go in and go into router 3 and do a show OSPF v3 neighbor. And we see that we actually have our adjacency established with router 1. Router 1's router ID is 1.1.1.1. And we can see our routes as well. We should see the 4 network, which is the loopback on router 4. We should see the 2.1, which is the IP address of the loopback on router 2. Remember, we didn't change the network type on that one, so it's being advertised with a 32 prefix because it's a loopback network. 145 is the link between router 1, 4, and 5, and 12 is the link between router 1 and 2. So that's what we should see in router 3. Show OSPF, show IP, OSPF IP route, OSPF v3, and that's what we see here. The 4 network, the 2.1, the 145, and the 12 subnet. These are coming in as OIA, again, because they're coming from another area in the autonomous system. Show IPv6 route, we should see the 12 network, the 22 network, the 44, and the 145. All right. So show IPv6 route OSPF, and we see the 12 network, the 22 network, the 44 network, and the 145 network. This is the link between router 1 and router 2. This is the loopback on router 2. This is the loopback on router 4. And this is the multi-access network between routers 1, 4, and 5. All right. Task 4, verify OSPF v3 configurations on router 1. Now again, the whole point of this exercise is to see the difference between doing our classic configuration verifications and our OSPF v3 configuration verifications. And we can see there is a difference, right? We're typically using the OSPF v3 command rather than saying show IP OSPF interface. We say show OSPF v3, and then we can specify whether we're looking at our v4 enabled interfaces or our v6 enabled interfaces. In this case, we're actually going to do both. So show, this is on router 1 actually. So let me pull up router 1. Show OSPF v3 IPv4 interface. Now the output here is exactly what we would expect to see if this was classic OSPF, right? We see the link local address, we see the IP address and the mask that's configured on the interface, we see the area that the interface is in, we see the process ID, we see the router ID, we see the network type. This is a Ethernet interface, so it's going to come up as network type broadcast. We see the cost of the interface. The metric for OSPF v3 is calculated exactly the same way as classic OSPF. We see who the DR is on this segment, router 5. We see who the BDR is on this segment, router 4. Standard timers as well. The dead timer is 40 seconds. The hello timer is 10 seconds. So all the theory that we learned about with OSPF in our lecture and all the theory that we learned about for OSPF in the Encore class applies here, right? OSPF v3 doesn't change the fundamental protocol itself. It changes how information is exchanged. It changes what transport we use to exchange information, but it doesn't change fundamentally how the protocol operates. The protocol is still going to operate as a standard OSPF protocol. Same thing with OSPF IPv6 interface. Ethernet 1.1 is going to be a broadcast interface. It's going to be in area 0. Serial 2.0 is going to be a point-to-point interface. That's because it is a serial interface running HDLC, and HDLC is a point-to-point protocol by default. That interface is in area 1. And we have our Ethernet 1.0 interface, which is also broadcast, and that's going to be in area 2. So basically it just tells us which interfaces are running the protocol, what address family they're a member of, what process they're a member of, what area they're a member of, what the network type is, and so on. So now if we open up router 5, router 5 is just kind of this router sitting off by itself in area 0. And I do a show IPv6 route OSPF, I can see all the prefixes that I would expect to see. This is the LAN between router 1 and 2. This is the subnet between router 1 and 3. This is the loopback interface on router 2, the loopback interface on router 3, the loopback interface on router 4. Notice that the router 4 route shows up as an O route because it's inside of area 0. Remember, this is a type 1 LSA route. This is an intra-area route, a route that I'm learning within my area. So that's going to have an O next to it. OIA indicates, or OI in this particular case because it's V6, indicates that this is an inter-area route or a type 3 prefix summary LSA, or what they call an inter-area prefix LSA in OSPF v3. All right. So the O, like I said, indicates that the route was learned internally within the area. OIA indicates these are routes that are learned from other areas. And it does match. Let's do a show OSPF v3 route, show IP route OSPF v3. There's the 4.0 subnet. There's the 3.1. Again, it's being advertised as a /32, even though it's a 24 on the interface, because OSPF always advertises loopbacks by default as /32, regardless of whatever's configured on the interface, unless you change the network type. We see that with the 2.1 loopback address as well. 13 subnet, 12 subnet. Again, router 1 to 2 and router 1 to 3. All right, notice the administrative distance values, the cost values are still calculated the same way. That hasn't changed. Next hop address is router 1, which makes sense because these are all OIA routes. Guess where the OIA routes are coming from? Router 1. Router 1 is the ABR. It's the one that's originating these prefixes into area 0. All right. Let's see, 4.0 is an example of an intra-area route from router 5's perspective. Router 2 and router 3, which are part of area 1 and 2, also are represented in router 5's routing table as intra-area routes. All right. And they're inserted into area 0 by router 1, which is the ABR, all the stuff I talked about. Prefixes 2.0 and 3.0 are the loopbacks of router 2 and router 3. They show up as /32s, even though they're technically /24s. But again, because OSPF treats loopback interfaces as loopbacks, in other words, it recognizes the interface as a loopback, it's going to automatically advertise a host route for that interface because technically a loopback really should only have one IP address anyway. There's no active hosts on that network. You could change that behavior if you modify the network type from loopback to point, and we would use the OSPF v3 network point-to-point command to do that. No reason, right? There's no reason actually to even assign other than a host route to the loopback anyway. In the case of our labs here, we're trying to simulate additional subnets by using those loopbacks, so we might want them to look like actual networks, so that might be a reason to do that in this particular case. All right. Now this is a brand new command that we haven't seen before. Show OSPF v3 rib. What we're looking at in this particular case is the routing information base for OSPF v3. Show OSPF v3 rib detail. Now the output is relatively easy to understand. It's telling us essentially basically what OSPF is being made aware of. The 12.0 subnet is an inter-area route. It has a cost of 74. It's in area 0. The originating router ID is 1.1.1.1, which makes sense because that's our ABR. And the ABR is responsible for generating type 1 or type 3 LSAs. All right. Here we're seeing the via is the next hop, the exit interface, and who's advertising the link state advertisement, router 1.1.1.1. All right. Same thing for the 13 subnet. The 145 is intra-area. The source is router 5. So I'm actually generating the LSA myself. That's why we see a via of quad 0. Via of quad 0 means self-originated. All right. Then the rest of these are going to be intra-area prefix LSAs. And then we see the rest of our V6 LSAs as well. Same concept. 12 is inter-area. 13 is inter-area. 145, which is right here, is intra-area. Again, via double colon is all zeros, indicating that I'm the one that's originating that LSA. All right. Now, I'm not the only one generating a type 1 LSA for the 145 subnet. Everybody that's connected to the 145 subnet would be generating the type 1 LSA. But who is the DR for that segment? Show OSPF v3 neighbors. I end up generating the advertisement for this prefix. Why? Because I am the DR. Router 4 on that segment is the BDR. Router 1 on that segment is the DR other. So if I was to go to router 4, actually let's just do it on router 1, show OSPF v3 rib detail, you would see for the 145 subnet, I'm not the originator. In fact, actually, in this case, for the 145 subnet, well, I'm listed as the source because, again, I'm attached to that prefix. I'm attached to that multi-access network, but I'm not responsible for managing that multi-access network. I'm not the DR for that segment. Again, show OSPF v3 neighbor. Router 5 is the DR for that Ethernet segment. So even though I'm participating in the broadcast domain, I'm still originating a type 1 LSA based on my attachment to that broadcast network. Router 5 is really the chief of that broadcast domain because it's the DR for that segment. All right. So we can see the difference between inter-area and intra-area and so on. All right, it gives us information about the area border routers, including who is the router ID. Not directly, right? If I go back to my output here, I don't see directly, let's go back to router 5 here. I don't see directly who is the ABR, but I can infer from this output who the ABR is. Based on the fact that this is an inter-area route, and the source is 1.1.1.1, I can then infer that that must be the ABR for this area. That's at least the ABR that's generating the prefix. If I had multiple ABRs, only one ABR is going to be responsible for identifying the existence of those inter-area routes. If both ABRs have access to the same external domains, we don't generate type 3 LSAs from every ABR unless it's a unique connection. In other words, the ABR is only connected to that, is the only ABR that's connected to that particular area. That's a little bit more of a CCIE discussion, which you guys are, by the way, now qualified to go take the lab because you passed Encore. You knew realize that Encore counts as your CCIE written. Yeah. So if you want to go and venture to take the lab, be kind of interesting. All right. So what about the adjacency process? Is it any different with OSPF v3? So let's go into router 3. We're going to do a debug OSPF v3 adjacency. All right. Notice it's going to turn on well, I did it for both stacks. I guess they're only doing it for IPv4. So let's do that instead. So our outputs look the same. Let's do it for just IPv4. All right. And we're going to do a clear OSPF v3 IPv4 process. Now, what I would expect to see is the transitions from the different states. I would expect to see the down state, the init state, the exstart state, sorry, the two-way state, the exstart state, exchange, loading, and full. We might not see a specific reference to each one of those, but we should see most of them, right? So interfaces going down, the neighbor went down, we lost our DR, BDR election, the neighbor detached, right? And then we had the neighbor come back up. Let me see, where did the neighbor, yeah, I guess right about here is where we, the process was reset. So now we're in the down state, right? This line actually represents the fact we've gone into the down state. So that's the initial state of OSPF. Now we're resetting the process. So now we're in let's see, interfaces going up, remembering the old DR. Remember that wait time we talked about in the Encore class? There's the wait time is tied to the same as the dead timer, 40 seconds in this case. So if the process restarts, we do remember some of the characteristics of who the DR and BDR are based on that. So it looks like the interface came up. OSPF started on the interface for loopback and Ethernet. I added 1.1 to my neighbor list, which means I've received a hello from that neighbor. So we move past the init state. The init state is where we don't see the init state is where we see a hello, but we don't necessarily see ourselves in the neighbor list of that hello packet. I added 1.1.1.1, which means I've moved to the two-way state. Two-way state, if you recall, means that my neighbor that I'm forming this adjacency with now lists me as a neighbor in their neighbor list in their hello packet. I list them as a neighbor in my neighbor list in the hello packet. So we know that we can become fully adjacent. We may stay in the state. Two-way is potentially a stable state, meaning that routers could stay in that state if they're both DR others. DR others don't go to a full state. They stay in a two-way state. We are not both DR others, so now we need to move into the X-start state. Right? We move from the two-way state to the X-start state, and you can see that, we didn't quite capture that here. You'll see a reference, we should see a reference to it right here. State X-start. So we're doing our DR BDR election. I'm sending a DBD, I'm receiving a DBD. Again, this is the whole point where we're trying to establish who's going to be the chief of communications, the master and the slave. I received a DBD, I sent a DBD, so now we're in that X-start state where we're actually negotiating who's going to become the master and the slave. And it says neighbor negotiation done, we are the master. All right, now we go to the exchange state. We can see exchange state listed here. Technically, the exchange state starts kind of right here. I'm sending a database descriptor packet, which is a summary of my link state database. You're sending a database descriptor packet, which is a summary of your link state database. So we're trying to identify what information we already have versus what information we don't have, so that we can start to do our actual route exchange, our actual LSAs. So again, that's the exchange state where I'm sending and receiving summary LSAs or summary database descriptors. The exchange is done. Now I'm in the loading state. Well, this is where loading is done, but now I'm transitioning to the loading state, and in the loading state, that's where we're synchronizing our actual databases. I send you a link state request for the stuff that I don't have that you have. You send me a link state update to include that routing information. And that would go in both directions. You would also send me a link state request, and I would send you a link state update. And that would allow us, this is the point in which we're actually exchanging routing information, the loading state. Once the loading state is done, we recognize that we're synchronized with the peer, and the state changes to full. So you do actually see kind of the whole progression, if you will, from down to init to two-way to X-start to exchange to loading to full. Turn off your debug. And they're breaking down the same steps here. Here's our X-start state, X-start, exchange, loading, full. All right. Now we know that we go through these different progressions from the down all the way up to the full state, and sometimes we'll stay in the two-way state. The idea, though, is that we are trying to synchronize our link state databases with the other routers within our area, and then other routers outside of the area will do a similar synchronization. We also know that on multi-access networks, we have to do a DR-BDR election. What was the purpose of the DR-BDR election on multi-access networks? To reduce the number of full adjacencies that we have to have, in turn reducing the amount of overhead for communication. The DR assumes the role of chief, if you will, on a multi-access network, and any topology changes have to be propagated to the DR, and then the DR is responsible for propagating those topology changes to the other routers in that multi-access network. All right, so they're kind of breaking down the different states. The first thing is to determine who the DR and BDR roles are so we can optimize the exchange of information. The next step, the routers start to exchange the content of their databases. So we're beyond the two-way state at this point. We've already done our master-slave negotiation. We've already decided who the DR and BDR are. Now we're doing our summary LSAs to determine if our databases are already synchronized, and if they're not synchronized, what pieces of information are required for us to complete that synchronization. All right, so next we start to exchange the content of the database. The first phase of this process is to determine the master-slave relationship, choose the initial sequence number for the adjacency information. All right, DBDs, or database descriptor packets, are what are used to facilitate this process. I receive a DBD, I transition the state of the neighbor from where the packet was received to the X-start state. I populate my database summary list with the LSAs described in the contents of the neighbor's database, and I send my own empty DBD packet. Basically, the idea here is that we are trying to establish what information do you know versus what information do I know. All right? It goes on further to say, okay, with this master-slave selection complete, the database exchange process can start. R3 transitions will transit R1's neighbor state to exchange, where we're actually doing the DBD exchanges. R3 describes its database to R1 by sending a DBD packet which contains all the headers of the LSAs, not the complete contents, right? What I like to refer to simply as a summary of the database. Why would I do that, by the way? Why would I just give you a summary of my database as opposed to just give you the whole database all at once? Because you probably have relationships with other routers, which means in the area, which means you've most likely already learned a lot of information from the domain. Why would I give you all of the information when you already know most of the information or even some of the information? So I'm going to give you a summary of my database so that you can then selectively decide what information you need versus what information you don't need. Again, just adding an additional level of efficiency to the overall communication process. All right? It describes the content of the database. The router compares the contents of its own summary list with what it received from the neighbor. If there are differences, it adds the missing LSAs into a link state request. At this point, we're now moved from the exchange state to the loading state, where we're actually exchanging prefix information and network layer reachability information. After that loading state is done, then we go into the full state. I mean, this is not new. We talked about this in the Encore class. What about the DR-BDR election process? The general concept, like I stated before, is on a multi-access network where I potentially have multiple peers, right? This multi-access network, I have 5 routers, so I potentially have 5 different peers. I want to reduce the number of total full adjacencies that I have, so I'm going to elect a chief. How is that chief selected? Technically speaking, it's really just the very first router that boots up. But there's actually 2 variables that are used to decide who the DR is. Do you guys remember what those variables were? What's the first thing that we use to decide who the DR is? Priority. Priority. Priority is the first thing that we use. Now, the default priority on all OSPF routers is 1. So if I don't modify the priority, yes, router ID would be used, but router ID is actually technically used as a tiebreaker. And in the case of OSPF, highest wins. Now, what did I mean by most likely it's just the router that boots up first? Because the process is non-preemptive, right? So if router 1 boots up and it has a low priority and a low router ID, but it just happens to be the first router that boots on the segment, it's going to become the DR. And even if another router comes along with a better value, we do not preempt the DR election. So router 1 would remain the DR even though it has inferior values configured. So we can kind of influence how the DR is selected. but we can't always guarantee who the DR is going to be. We can certainly guarantee who the DR is not going to be. We have an option to configure a priority of 0. And a priority of 0 means you can never be selected as the DR or the BDR. All right? The overall idea here is that we're trying to reduce the amount of update traffic. We're also managing the synchronization of the database by having a central point to control how that information gets collected and then how that information gets disseminated to the other routers in the multi-access network. If the DR fails, we have already elected a BDR. The BDR would take over the role of the DR, and some other BDR would be elected at that point. So let's take a look at router 1, router 4, and router 5. We're just going to do a show OSPF v3 neighbor. Router 1, I'm going to start with router 5 since I'm closest to that. Show OSPF v3 neighbor. Now I can see that I'm neighbors with router 1 and router 4. Priorities are set to 1. That happens to be the default priority per neighbor. All right. I can also see that router 4 is the BDR. Router 1 is the DR other. Now if I was to do a clear OSPF v3 IPv4 process, I should lose my role as the DR. And router 4 should become the DR. Give it a second here. I only cleared the v4 process. I didn't clear the v6 process. We're still going through the exchange information. But eventually, I should see router 4 as the DR. Come on, you can do it. DR other is just any router that's not a DR or a BDR. There we go, we got our adjacencies. So now you can see that router 4 became the DR. Now here's an interesting question. How come router 1 didn't become the BDR? Router 5 got reset, right? So it lost its role as the DR, right? So shouldn't router 1 have kind of automatically been promoted to the BDR? Because we didn't have a BDR at that point. Router 4 was the BDR, but router 5 ended up becoming the BDR. And here's the reason why. Show OSPF IPv4 interface. There's a timer here called a wait time. And that wait time protects who becomes the BDR. So as long as router 5 were to go down and come back up within that 40-second window, it can still claim the role as the BDR. If the BDR were to go down, the currently elected BDR, which happens to be router 5 now, if router 5 were to go down, as long as it comes up within a 40-second window, as long as the OSPF process is running within a 40-second window, it will maintain its status as the BDR. But if I go into interface Ethernet 1.0 and I shut that interface down, all right, so I've disconnected router 5 from the network. Now I'm going to try and talk for about 40 seconds because the idea is that I want to see after that 40-second timer has expired, router 1 should become the BDR, and router 5 would then become a DR other. All right, so let's do a no shut. Hopefully that was 40 seconds. Our adjacencies should eventually come back up. The interface came up. It might take a couple of seconds for the adjacencies to come up. There's our adjacencies. So now I should see, in this case, that router 1 became the BDR. And if router 4 is the DR and router 1 is the BDR, that means I must be a DR other. This behavior only applies to the BDR. It does not apply to the DR. If the DR goes down, somebody else has to become the DR right away. We're not going to wait 40 seconds for a new DR to be elected, because then OSPF would be broken for 40 seconds. But so that wait timer really only applies to the BDR election. So if router 1 were to go down, as long as router 1 came back up within that 40-second window, it would still maintain its role as the BDR. Okay? So it's not truly a cascading election, right? We don't say DR goes down, BDR gets promoted, we pick the next BDR. It depends on whether or not we're within that 40-second window or not. Okay? We don't really need to run the neighbor command on the other routers. I mean, they're just going to reflect the same information or similar information. All right? They mentioned all the stuff that I talked about here. The only thing that they mention here that I didn't mention is how I communicate. When I'm sending packets to any OSPF router, I address them to 224.0.0.5. If I'm sending a packet to the DR, it's addressed as 224.0.0.6. That is the well-known multicast group for all DR routers. Now, if we look at our topology here, we can see that router 4 is the DR on Ethernet 1.0. So if I go to router 4, we put these in order. Got 2 router 3s. Let me go ahead and load up router 4. There's, a couple of interesting ways that you can identify who the DR and BDR is. The show IP OSPF interface is perfect, or show OSPF v3 interface. But I could also do this, show interface Ethernet 1.0. Show IP interface Ethernet 1.0. And you'll notice in this case, show interface Ethernet 1.0, show IP interface Ethernet 1.0. Why am I not seeing that? Hold on one second. Show IP interface brief. It is Ethernet 1.0. What I should be seeing, stupid. I don't see this in IPv4. I see it in IPv6. So let's do it in IPv6. Show IPv6 interface Ethernet 1.0. And what I was going to try and demonstrate here was I know this router is the DR because of this. It's joined the DR multicast group. It's always going to be a member of all routers, all OSPF routers multicast group. 5 is basically everybody. Every OSPF router joins that group. 6 is DRs only. So just by running this command, I'm able to determine that this is in fact the DR, at least in IPv6, for this particular broadcast domain. All right, if I was to do that on router 5, show IPv6 interface Ethernet 1.0, we would see that router 5 did not join the 6 group. It's only joined the 5 group. All right. In the topology, R5 was elected as the DR. Well, we kind of played around with that, so we flipped it around a little bit. Router 4 became the DR, router 1 became the BDR. And what they're doing here, I'm not going to do this because we already did this, is they're basically shutting down the interface to see that election change, right? They're shutting down the interface to see who gets promoted to the DR and who becomes the BDR. And sure enough, router 4 did get elected as the DR. And in the case of router 1's adjacency, remember router 1 has multiple areas. So this is a DR election in a completely different broadcast domain. Remember, this DR-BDR election process occurs per broadcast domain, not per OSPF area, not per autonomous system, but per broadcast domain. Router 1 happens to be a member of 2 separate broadcast networks, which means there are 2 separate elections that affect router 1's domain. All right. Now, whether or not router 1 becomes the BDR or not, again, it will be dependent upon that wait time. Had we waited 40 seconds, yes, router 1 would have become the DR. And that's what we did in our demonstration. Router 1 became the BDR because we exceeded that 40-second wait time window. All right? They do a no-shut. Now, what they're demonstrating here is what we've already done as well. When router 5 comes back, even though it has the highest router ID for the segment, it does not reclaim its role as the DR because this selection process is completely non-preemptive. So show OSPF v3 neighbor, router 4 remained the DR, router 5 actually became a DR other. DR other is basically just, hey, you're not a DR, you're not a BDR, you're kind of just one of those other routers in the segment. So even if I go into router 5, let me show you this real quick, and I go into interface Ethernet 1.0. Remember, we're running OSPF v3, so we're going to use OSPF v3 for every single command now. OSPF v3 priority 200. I've set the priority for the interface in the broadcast domain. And if I go to router 4, show OSPF v3 neighbor, I can see that router 5 is advertising the highest priority for the broadcast domain. It's advertising a priority of 200. But it still didn't become the DR because, again, the election process is non-preemptive. But it's a good point to note here that because we're now running OSPF v3 address family mode, everything we do based on adjusting timers or setting a priority or setting network type or whatever, it's all going to be OSPF v3. So if we say network point to point, so we're placing IP OSPF or IPv6 OSPF with simply OSPF v3. All the syntax is still the same. All the commands are still the same. The effect of the command is still the same. But rather than saying IP OSPF priority or IPv6 OSPF priority, we simply say OSPF v3 priority. Here's the other benefit to that, by the way. I only did it one time, right? But it changed it. Let's go to router 4 again. It changed it for both address families, for v4 and v6. Now I could come in here, I believe, if I'm correct, OSPF v3, OSPF v3, OSPF v3, and I could say priority 200. Yeah, see, it doesn't even give me the option to change it per stack. In other words, it doesn't give me the option to change it because normally I would say OSPF v3 and then I could say IPv4 or IPv6. Yeah, even with the timers, it doesn't allow me to change it per stack. So, and again, that makes sense, doesn't it? Why does that make sense? Because we're not actually forming a v4 adjacency. Remember, with OSPF v3, we're only forming a v6 adjacency. We're transporting all the v4 reachability information between the routers over the v6 adjacency. So it makes sense that we can't adjust these values per stack because the relationship is going to be v6. The adjacency is going to be v6. All right? And they're going through the whole concept. When you re-enable R5, Ethernet 1.0, new election takes place. We did all that. All right. By the way, that priority is sent in the hello packet. The router with the highest priority will be elected as the DR. No, that's not true. That's the configured behavior. But again, it really depends on who boots up first because it's non-preemptive. It's more likely that you'll become the DR. If you happen to boot up first, you'll certainly become the DR, but just because you have the highest priority does not guarantee that you're going to become the DR. The second highest OSPF priority is elected as the BDR, same thing there. The router with a priority of 0, this is absolutely true. There's no exception to this rule. If you have a priority of 0, you can never be elected. Now, this was actually on the Encore test, but in our topology here, would I really need to have a DR-BDR election on this Ethernet link between router 1 and router 3? It is a multi-access network because it is Ethernet. And OSPF doesn't care if there's only 2 routers. If it's a type broadcast, if the network is type broadcast, I'm going to do a DR-BDR election. But I technically don't really need a DR-BDR election on that link, do I? What could I do to allow the adjacency to still form, but get rid of the need for a DR-BDR election? If I set the priority to 0 on the routers, we cannot form an adjacency. Because if the network type is broadcast and I put the priority of 0 on both interfaces, there's no full adjacency ever established. I need to change the network type. If I change the network type to point, then no DR-BDR election is required. Does that save me a lot? Not really. I mean, it doesn't really save me much. Even if I change the priority, if I left this as broadcast, I change the priority of router 3 to 0. Router 1 would still claim the DR role. Because in a broadcast network, you have to have a DR. Only routers that are DRs form full adjacencies with other routers. So you could make it so that router 3 doesn't ever become the DR by setting the priority of this interface to 0. But you could not set both interfaces to 0 unless the network type is point-to-point. Then it automatically sets the priorities to 0 because on a point-to-point link, there is no DR-BDR election. I don't know if you guys recall that question on that test. It was saying, I don't want a DR-BDR election on this Ethernet link. What do I do? Change the network type to point-to-point. All right? Remember, point to anything. Point to anything, no DR-BDR election. So same thing, they just want us to change the priority. I'm actually not going to do this because we already did this on router 5, but again, we're using OSPF v3 to change the priority. We did this on router 5, we changed it to 200. They're clearing the process on router 4 in the hopes that router 1 now becomes the DR. And in this case, router 1 did become the DR, not necessarily because it had the highest priority. Well, actually in this case, yes, because it had the highest priority. But had we had a BDR, and router 1 wasn't the BDR, even with a priority of 100, router 1 would not have become the BDR. Let me show you what I mean. So in our network here, do show OSPF v3 neighbors. Router 4 is the DR, right? Router 1 is the BDR. Router 5 has a priority of 200. So this is the exact scenario that they're describing in the text. Router 4 is the DR. Router 1 is the BDR. Now you would think that if I reset router 4, that because router 5 has a priority of 200, it should take over the role as the BDR, as the DR. But it won't. So let's clear the process, clear OSPF v3 IPv4 process. Yes. Go back to router 5. Look who became the DR. Router 1. There's no exception. If the DR fails and there is a BDR, the BDR always takes over the role as the DR. Even if somebody down the line has a better value. Now, we lost our BDR because it became the DR, which means technically now we don't have a BDR anymore. That's when router 5 gets into the loop now, because now router 5 becomes the BDR. What's the moral of the story? We should have had a drinking game. Every time I said DR, you should have had to drink something, right? No, the moral of the story is that you really can't control this election process. You can influence the election process, but in reality, you know, if a router happens to go down in the middle of the night or something, it's going to change. The election's going to change, and the only way to fix it is to reboot all the routers in sequence that you want them to boot up so that the DR becomes the router that you want, right? The only other option is to make all the other routers 0 and make only one router with a priority of non-zero. But that's a very dangerous proposition because then you don't have a backup. So typically what we will do in a network that we have multiple routers, 4 or 5 or 6 different routers, we will typically say, okay, we're not going to lose 2 routers. We might lose 1, but the likelihood of losing 2, so we might set the priority on all but 2 routers to 0, and then just allow the election to swap back and forth between the 2 routers that we know we want to control the domain. You know what I'm saying? Maybe they're the 2 routers that have the most amount of memory, or they have the high, faster CPU, or maybe they're geographically or physically in a place where that makes more sense for them to become designated for a segment. But again, that's a topology decision. That's based on what your topology looks like. All right? We know what the effect of setting the priority to 0 is. 0 means you can never be elected. So they did that on router 4 and router 5. You still show up as a DR other, but you can never be elected as the chief. This is, again, very dangerous because now we don't have a BDR. Router 1 would become the DR, and we don't have a backup. So if router 1 reboots, the whole broadcast domain stops working. And if it's a transit network for the rest of our OSPF area, that makes it even worse because now LSAs aren't going across the transit network, which means they're not going to the rest of the world. Well, at least the rest of the routers within the area. All right. Let's see here. Priority of 100, this guy became the DR. DR other routers. So this is interesting. I could see why they wanted to kind of demonstrate this. Interface Ethernet 1.0, OSPF v3, priority 0. And we do the same thing on router 4. Interface Ethernet 1.0, OSPF v3, priority 0. Do show OSPF v3 neighbor. OSPF. Notice that we're in a two-way state. Because router 4's priority is 0 and router 5's priority is 0, they can never progress beyond the two-way state because they're both DR others. See what I'm saying? But watch what happens when I clear the process on router 1. Clear OSPF v3 IPv4 process, right? The whole network resets. We didn't see it quickly enough, but do show OSPF v3 neighbor. For some reason I cannot type OSPF today. We didn't do it quickly enough, but the point is that, well, actually the network's not working right now, right? We're still in the xstart state, and we're still in the xstart state, so we're still in the xstart state. So until router 1 forms a full adjacency with the other routers, nothing is being exchanged in this domain because we didn't have a BDR to take over the role.
So clearing the OSPF process does that?
Clearing the OSPF process resets OSPF on the router. But because, the point is, because I didn't have a BDR, until that router boots back up and starts the process again and forms a full adjacency, the whole broadcast domain is broken. You'll always know that router 1 will become the DR, but if router 1 reboots or the OSPF process restarts, nobody's there to take over the role of the DR, which means that the network stops working. Probably not a good choice. All right. So the last task that we have here is to modify the timers. Remember, the timers in OSPF play a very significant role. Obviously, they determine how long adjacencies can last if I don't get hellos based on the dead timer, or how often hellos are sent. But two reasons why the timers are important in OSPF. First of all, they have to match in order for us to form an adjacency. That's number one. Number two, and this is also important, based on the network type, the timers will potentially change. So broadcast links and point-to-point links have a default hello interval of 10 seconds. All other OSPF networks, 30 seconds. And it's actually, by the way, pretty common. I wouldn't say common, but it's not rare, right? Where you might have mismatched network types. We see this a lot in like non-broadcast multi-access point-to-multipoint networks. So like you've got a point-to-multipoint frame relay network. The spoke routers are all your point-to-point routers, and the hub router is your point-to-multipoint. Well, guess what? The point-to-multipoint is going to have a default timer of 30 seconds. The point-to-point interfaces are going to have a timer of 10 seconds, which means that they're not going to be able to form an adjacency. All right? So what do you do in that case? If you have to have those network types identified, you need to manually adjust the timers so that the timers match. All right? And the default dead timer is always going to be 4 times whatever the hello interval is. All right? So we can run a debug to see if there's a timer mismatch. That's probably what they're going to have us do in this particular case. All right? Remember, there's technically six different network types. Point-to-point, no DR, BDR election, automatic neighbor discovery is allowed, 10-second timer. Point-to-multipoint, no DR, BDR election, automatic neighbor discovery is allowed, 30-second hello timer. Broadcast, automatic neighbor discovery is allowed, DR, BDR election, 10-second timer. Point-to-multipoint non-broadcast, no automatic neighbor discovery because it's non-broadcast. It is still point-to-multipoint, which means a 30-second timer and a DR, BDR election occurs. Remember what I told you guys, point to anything. Sorry, DR, BDR election does not occur. Point to anything means there's no DR, BDR election. Any non-broadcast means there's no automatic neighbor discovery. So non-broadcast, which is NBMA, 30-second timer, no automatic neighbor discovery, but we would have a DR, BDR election because it's not point to something. And then loopback is just treated as loopback. So those are the 6 network types: broadcast, non-broadcast, point-to-point, point-to-multipoint, point-to-multipoint non-broadcast, and loopback. So you guys think you can recite all that? No? Yeah. It takes a while to get used to it. The bottom line is network types do not have to match to form an adjacency. Right? Network types do not have to match. So for example, if I come out to my topology here, this is a R1 and R3. This is a broadcast network. I'm going to change R3's Ethernet 1.0 to point-to-point. And let's see if the adjacency breaks. Let me close this here. All right. Config T. Interface Ethernet 1.0, OSPF v3, network, point-to-point. All right. Went from full to down, loading to full. Interesting. Do show OSPF v3 neighbor. Oops. I've got a full state with router 1. Router 1 is broadcast. This guy is point to point. Notice my priority is 0. But from router 1's perspective, it doesn't care. Because router 1 says, well, I'm a broadcast, so I'm going to go ahead and elect myself as a DR. Automatic neighbor discovery is allowed in broadcast and point to point. So these guys can automatically discover each other, and their timers happen to match. The timer, the default timer for broadcast is 10 seconds. The default timer for point to point is 10 seconds. So the network type doesn't actually have to match. Now, what if I change it to non-broadcast? OSPF v3, network, non-broadcast. We will lose our adjacency, and the adjacency will not come back. And it's not that the adjacency won't come back because automatic neighbor discovery is not allowed on non-broadcast. Lisa is broadcast, I'm non-broadcast. Lisa's going to send out a hello packet. I'm going to see that hello packet, and I'm going to use that hello packet to form a unicast adjacency with Lisa. So we can still initiate the adjacency from one side of the link. But here's the problem. Do show OSPF v3 interface, Ethernet 1.0, the timer's changed. For non-broadcast, the default timer is 30 seconds. So guess what I do? OSPF v3, hello interval 10. Let's see if we get an adjacency, and we did. There was a question on the Encore test about which two network types would form an adjacency. They didn't give you any other information. They just said which two network types would form an adjacency. Now, I would have to assume in that particular question they mean without any other changes, right? Without changing any other configs. And that would be broadcast and point to point. We demonstrated that because they use the same timers. But technically, all of these network types are compatible with each other, as long as you manipulate the configuration slightly so that either the timers match or you statically define neighbors or whatever it might be. All right? So why does OSPF have all these different network types? Because OSPF treats itself differently based on what the underlying transport looks like. EIGRP doesn't care what the underlying transport is. OSPF is a little bit more cognizant about whether or not the underlying transport supports broadcasts or doesn't support broadcast. If it's a multi-point frame relay network, we don't want the spoke routers to become DRs because they don't have a full mesh. They're only hub and spoke, so they're not going to be DRs. So point-to-point network type is perfect for them because that means they get a priority of 0. You know, all these things were considered based on the network type. The bottom line, though, is that you can still communicate. You can still form adjacencies even though the network types don't match. You just might have to adjust the timers and stuff like that. All right, so if I do show OSPF interface here, we can see we're still non-broadcast, which basically means what? It tells OSPF this router cannot automatically discover its peer. We have to either statically define the neighbor or we have to respond to some sort of neighbor request. If I go to router 1 and I go to interface Ethernet 1.0 and I see OSPF v3, network non-broadcast, I'm going to lose my adjacency again because, again, the timers don't match. So I go ahead and make the timer match, and I still should not get an adjacency. Why am I not? Now the timers match, even the network types match. Why am I not getting an adjacency now? they're both non-broadcast, which means they're both not sending hellos because they don't have neighbors statically defined. Meaning, if it's non-broadcast, it means no multicast. So what I can do is I can go into OSPF v3 router, OSPF v3, router OS. Hey, we got a neighbor? This is not supposed to happen. But what we could do to fix this problem, I think it's probably because, well, actually we only got a neighbor for v6. We didn't get a neighbor for v4. v6 makes sense because adjacencies in v6 are done with link local. But, oh, we did get a neighbor for v4. Dang it. What I was going to say, let me do a clear OSPF v3 process. Oops. Typically what you would have to do, yeah, it keeps coming. Well, we got 2. Now 3 is down. So typically what you would have to do is you'd have to go into OSPF v3, go into the address family for IPv4 unicast, and you would use the neighbor command to specify the neighbor. I haven't done this in v3 in a while, so let me see where that would be. I wonder if it would be on the interface. It's a good question. It would be an interface command, OSPF v3 neighbor, and we'd specify the neighbor statically. Now I know why it's working. Here's the reason why. If this was classic mode, it wouldn't work. But it's working in IPv6 because the v4 neighbor relationship is automatically going to happen if the v6 neighbor relationship happens, because we're establishing the neighbor adjacency over v6. And we're using link local addresses to establish the adjacency. So we're not actually using unicast IPv4 addresses to establish the adjacency. If for some reason you had to statically define the neighbor, though, I found it's under the interface, OSPF v3 neighbor, and then you would specify the address of the neighbor. By the way, this could be specified as link local, or it could be specified as global unicast. All right? Actually, no, only link local, excuse me. We never establish adjacencies with global unicast. So it can only be a link local address. All right? That's way beyond the scope of what they were talking about in the book here, but you get the idea. Pay attention to the network types, because when you modify the network types, it modifies potentially the timers. You may also decide that you want to change the timers for other reasons. Maybe you're trying to get faster convergence. Maybe you're trying to identify dead peers quicker or something like that. Again, I would typically use BFD for something like that, but you could adjust the timers. Just make sure that you adjust the timers equally between the neighbors. Otherwise, the adjacency will fail. The default interval is 4 times. You don't have to make it 4 times. Clearly, this is not 4 times, but it is typically 4 times. So what they did is they just changed it on router 1. We're not going to do this because we already did a lot of that. And they changed it on router 2, and the neighbor adjacency came back up. All right? So that is it for that discovery. Let's get into our next section here, and then we'll see you guys in the next discovery. All right, now that we've gone through that discovery, we will have other discoveries as well as we go through our exploration of OSPF, but let's go ahead and start talking about the different LSA types. As we've talked about previously, it is very important for OSPF routers to share information about the different links in our topology. And one of the ways that we do that, or the primary way that we do that, is by sharing link state advertisements. Now, as we go through this section, I want to focus on 3 primary things about different LSA types. All right? And the first thing I want to focus on is who generates a particular type of LSA. So as we go through each type, we'll talk about which router is responsible for generating that type of LSA. The next thing we'll talk about is what is the general purpose of that particular LSA? Why is it important for us to capture that information? And we'll do a discovery in which we actually go and take a look at the different LSA types, and we look at in detail what those LSAs include. And then the last thing that we'll talk about is what is the scope of a particular link state advertisement, right? That means where within the OSPF autonomous system will that LSA be able to travel? Is it going to stay within the area? Is it going to move from one area to the other? Is it going to be allowed to move into special area types and so on? All right, so what we're looking at in this table here is we are looking at various LSA types. We have our router LSAs, we have our network LSAs, we have our summary LSAs, our ASBR summary LSAs, an autonomous system LSA, and then we have some other types as well. We'll talk about what those other types are a little bit later on, but we're going to focus on the primary LSA types for now, okay? And as we go through this discussion, again, just keep in mind that we are going to be focusing our attention on who's generating these types of LSAs, what is the purpose of those particular LSA types, and what is the scope. So we can see from this diagram here that we do actually see a representation of scope here. For example, a type 5 LSA generated by an ASBR is going to have an inter-area scope, meaning that that type 5 LSA is going to be able to pass from its originating area into the backbone and then ultimately into other areas as well. Now, there are some limitations as to where those type 5 LSAs can go when it comes to special area types, but we'll talk about that a little bit later on. Another example, type 1 or type 2 LSAs, in this particular case represented here, those are what we call intra-area LSAs. So they're generated within the area and they have to stay within the area. I'm not going to break down each one of these here because we're going to spend some time talking about each of these LSA types as we go through our discovery and as we go through the rest of this section here. All right. So let's talk about the three things that we were talking about. We were going to talk about as we talk about each of these LSA. Type 1 LSAs. Every single router within OSPF generates type 1 LSAs. All right. We know that the type 1 LSAs, well, we don't know this yet, but we're going to see this as we go through our discovery. But type 1 LSAs describe the links that the router owns. So depending on how many actual interfaces a device will have, how many networks it's participating in, will depend on how many type 1 LSAs it's generated. But the scope of these type 1 LSAs are intra-area, meaning they will never leave the area. Every single area. It doesn't matter if it's the backbone, it doesn't matter if it's a normal area, it doesn't matter if it's a special area type, we'll have these type 1 LSAs. For all types of LSAs, we have a LSA header. We'll see this in a Wireshark capture a little bit later on as we kind of go into our discovery. But one of the fields in that LSA header is a link ID or a link state ID. In the case of type 1 LSAs, that link state ID is the actual router ID of the router that's generating those type 1 LSAs. Our type 2 LSAs, these are special LSA types as well. Well, they're all kind of special in their own right, I suppose, but who generates a type 2 LSA? DRs and BDRs generate type 2 LSAs. DRs and BDRs generate type 2 LSAs. And what is the purpose of those type 2 LSAs? The purpose of a type 2 LSA is to describe the designated router that, I should say the broadcast domain that the designated router is responsible for. All right. So in other words, what is the network? What is the mask of that broadcast domain? And then on top of that, who are the participating members of that broadcast domain based on their router ID? These types of LSAs are only flooded within the area. They are intra-area LSAs. They do not leave the area. And again, as we go through our discovery, we're going to go ahead and look at these LSAs in the database. We'll take a look at what they look like and what kind of information is contained within that LSA. The link state ID of these type 2 LSAs is the actual IP interface address of the DR. So it's not the router ID of the DR, it is the IP address of the interface that is connected to that broadcast domain. Our type 3 LSAs, these are inter-area LSAs, meaning that these LSAs will propagate throughout the entire OSPF autonomous system. The exception to that is for particular special area types, namely a totally stubby area or a totally not so stubby area. Who is going to generate these type 3 LSAs? The area border routers. They're the ones that are generating these type 3 LSAs. And the purpose of a type 3 LSA is to act as a summary of my type 1 and type 2 LSAs. Summarization does not happen automatically in OSPF. Really doesn't happen automatically in EIGRP anymore. It used to, but more modern implementations of EIGRP don't do automatic summarization. But in any case, in the context of OSPF, summarization is only done manually. It does not occur otherwise. And there's only two types of routers that we can summarize on in OSPF, and that is our ABR and our ASBR. All right, but the ABR is going to be responsible for generating these type 3 LSAs. Those type 3 LSAs will propagate beyond the area. They'll move throughout the entire OSPF autonomous system, with the exception, like I said, of particular special area types. The link state ID of the type 3 LSA is the destination network number. And again, we'll see that as we go through the process of looking at this in our discovery. Now, the last two LSA types that we see here on the screen are type 4 and type 5. Interestingly enough, these LSAs are directly related to each other. I'll talk about type 5 LSAs first, and then we'll talk about the type 4 LSAs. So type 5 LSAs are generated by autonomous system boundary routers. And the purpose of these type 5 LSAs is to describe the external networks that are being redistributed into OSPF. Okay? So actually they represent the actual networks that are being redistributed into OSPF. And the scope of these type 5 LSAs is inter-area, meaning that they will propagate beyond the area where the ASBR is attached. They'll move into the backbone and they'll move into other areas as well. Okay? The only exception to that is special area types. We never see any type 5 LSAs in special area types. That would be stub, totally stubby, not so stubby, and totally not so stubby. Now, let's talk about type 4 LSAs. Type 4 LSAs will not exist unless you have type 5 LSAs, and they will not exist unless you have a multi-area design. It is a little bit difficult to kind of visualize what a type 4 LSA does, so what I'm going to do is draw a quick little diagram here. Let's say that I have an area here, and there's an ASBR attached to this area, right? So I'm generating my type 5s into that area. And then I have my backbone area, and I've got an ABR here, okay? So those type 5s will continue to propagate, and they'll move through the autonomous system. The ABR, which is attached to the area that has the ASBR, is going to generate these type 4 LSAs into the backbone or into the other areas, away from where the ASBR is attached, essentially. So in this case, we're going to, if this is area 1 and this is area 0, we're going to generate those type 4 LSAs into area 0. If you were to look at a type 5 LSA, you would see that it does contain information about those external prefixes that are being redistributed, but it doesn't necessarily contain any specific reachability information. It identifies the router ID of the originating router, and that's going to be listed in the OSPF database. but it doesn't really describe how to get to that ASBR. So the purpose of a type 4 LSA, which is called an ASBR summary link advertisement, is to let everybody else in the OSPF autonomous system know how to reach that particular ASBR. Within Area 1, we don't need the type 4s because within Area 1, we're using the actual type 1s to reach the ASBR because we're participating within that area. But everybody else outside of that area is not going to know how to necessarily reach that particular ASBR. We'll get into this in more detail. I keep saying that, but we definitely will see this in more detail. One of the things I want to point out is how we deal with metrics and how we deal with routing to these external prefixes that are being redistributed, and how we utilize essentially the type 4 LSAs to define how we're going to reach a particular ASBR, and we simply use the type 5 LSAs to identify that those external prefixes exist. Okay? We do have some other LSA types, type 6 LSAs that are used for OSPF multicast applications. Type 7, essentially type 5's cousin, if you will. In fact, they're pretty much identical to type 5 LSAs. The only difference is these are LSAs that are generated by an ASBR that is attached to a special area type, like a not so stubby area and a totally not so stubby area, or a total NSSA. All right. We will also spend quite a bit of time talking about type 8s and 9s. Type 8s and 9s. Type 8 LSAs and type 9 LSAs are used for OSPF v3. The type 8s are used for link local addressing scopes and to identify not only the FE80 or the link local scopes in IPv6, but also the unicast scopes, right? The global unicast scopes. So we'll see that as well when we go through our discovery. And then we have the type 9 LSAs. Now, interestingly enough, type 1s and type 9s in IPv6 are related to each other. A type 1 LSA in IPv6 doesn't actually contain any prefix information. It contains router information, and it allows us to see that router information, but it doesn't actually contain prefix information. So we use these type 9s, which are called intra-area prefix LSAs, to identify the prefix information for those type 1 LSAs. So you will not see type 9s if you're not running OSPF v3 or if you're not running OSPF for IPv6. Okay? So if we go back to the diagram here, we can kind of see, again, what we were talking about previously. The type 3s are going to go between the areas. 1s and 2s are going to stay within the area. Type 4s are going to be generated by the ABR. This is our ABR into the area away from where my ASBR is attached. And again, this is to describe how to reach the ASBR. And then these are my external networks. And this identifies those particular external networks. All right. It's a really exciting kind of conversation because essentially this is really how OSPF functions. It's a very important concept. This linked state database is what OSPF is learning, and it provides that functionality for OSPF and the OSPF operations. Now, what you're seeing on this particular table here is just kind of a comparison of the OSPF v2 LSA designations and how they're identified versus OSPF v3. We can see that for our router LSAs, they're pretty much the same, type 1. We use a hex representation for the router LSAs, hex 2001. And then we have the network LSAs, which are my type 2 LSAs. We have our network summary LSAs in OSPF v2. These are called inter-area prefix LSAs in OSPF v3. Again, these type 2, type 3, type 4, type 5, etc. We have our ASBR summary LSAs. These are my type 4s in OSPF v3. These are called inter-area router LSAs. We have our AS external LSAs, which are those external routes that are being redistributed into OSPF. Those are called AS external LSAs, multicast type 7 LSAs, which are NSSA external. This would be an ASBR generating LSAs into OSPF from a redistribution process into a special area type, NSSA or totally NSSA. And then we have our two IPv6 related LSA types. All right. Now, most of the functionality of OSPF v3, and we've already seen this through some of our discussions, is pretty much the same. And we saw the exception to that as maybe some of the LSA types are renamed. But here are the descriptions, the detailed descriptions of these different LSA types. Inter-area prefix LSAs for ABRs. These are my type 3s, just kind of renamed. They pretty much look exactly the same. These are my summary LSAs that are represented by summarization that occurs on the ASBR, or excuse me, the ABR. In OSPF v3, these are based on prefix and prefix length, which is essentially network ID and subnet mask instead of address and mask, but it's pretty much the same representation. And obviously a default route doesn't really have a mask. It's going to have a prefix length of 0. Then we have our inter-area router LSAs for ASBRs. These are my type 4s. And again, these describe how we're supposed to get to, or what is the location of the ASBR. All right. And again, the ABR that is attached to the area that has an ASBR is going to generate those type 4 LSAs outside of that area for the rest of the domain so that they can identify how they're going to reach that ASBR. All right. And the two new LSA types that we talked about, these are my type 8s and my type 9s. The type 8 LSAs, these are my link LSAs. They have a link local flooding scope. That's a very interesting concept. This is the only LSA type that isn't defined as an inter-area or intra-area scoped LSA. These are link local scoped, meaning they're only going to go out the wire essentially to the neighboring router. They're never flooded beyond the link. Essentially, these provide the link local address of the interfaces that are participating in OSPF, and they let the other routers that are peers know about the list of prefixes that are tied to that particular link. They also allow the router to identify different types of bits, and we'll see this in our discovery, that allow us to identify how those LSAs are being propagated and originated into OSPF. All right. And then we have our intra-area prefix LSAs, which are our type 9 LSAs. And again, these are associated with our type 1 LSAs to describe the prefixes within the area, particularly the prefixes that are being generated or identified by, or excuse me, attached to a local node within that area. Okay, so if you look at the diagram here, this is a representation of an OSPF v3 network. We can see that our network and router LSAs are intra-area. Our inter-area prefix LSAs will move beyond the area. Those are our type 3s. And our inter-area router LSAs are our type 4s. They're going to get generated by the ABR attached to an area that has an ASBR, and our AS external LSAs are going to move beyond the area as well. These are the type 5s that are generated by the ASBR within a normal area type. All right. So what we're going to do next is we are going to jump into discovery number 7, and we're going to take a look at the details of the link state database. So we'll see you guys there.
So we're moving into discovery number 7, and discovery number 7, we're going to kind of do a deep dive into looking at the link state database for OSPF. We'll take a look at all the different LSA types, the router LSAs, network LSAs, summary LSAs, ASB summary LSAs. We will even see some of the type 5s because we've got an external router here that's actually generating some type 5 LSAs as well. Router 3 is acting as an ASBR in this particular topology. So we're going to take a look at all of the different LSA types, and we're going to kind of correlate how those LSAs are reflected in the database and how they're reflected in the topology. All right, so we'll go in and take a look at that. We'll take a look at all the OSPF v3 the OSPF v3 database as well. It's going to be slightly different in that it's going to contain a lot of the v6 related LSAs as well, which are the type 8s and type 9s. So we'll take a look at that as well. But we're going to essentially break it down per area based on which types of routers are generating what types of LSAs. So router 4 and router 1 are in area 1, or excuse me, area 0, and that is an Ethernet link. So we know there's going to be at least type 1 LSAs there. There's going to be type 2 LSAs because there's going to be a DR-BDR election between router 4 and router 1. There will be type 3 LSAs in that area because we have LSAs coming from other areas, right? We'll also have type 4 LSAs. R1 is going to be generating a type 4 LSA because there's an ASBR attached to area 2. And remember, the ABR that is attached to the area that has an ASBR is going to be generating type 4 LSAs into the other areas outside of the area that the ASBR is actually attached to, right? So we won't have type 4s in area 2. But we will have type 4s in area 1 and area 0. Of course, router 3 is acting as an ASBR, so we're going to have our type 5s as well. The type 5s will exist in all 3 areas because they originate in area 2, and then they get propagated into area 0 and area 1, respectively. We may or may not have some type 2s in area 1. We'll certainly have some type 2s in area 2 because we see a multi-access network there. We have a point-to-point serial link between router 1 and router 2, so most likely we won't see any type 2s in that area, but we would definitely see type 1s, type 3s, type 4s, and type 5s. And that's really our goal, right? And of course we'll see type 8s and 9s as well because we have IPv6 enabled. So we're going to see type 8s and 9s as well. So our goal is basically just to kind of go through the entire topology and do a deep dive into the database, and then we'll move on to our next lesson and we'll get into special area types and authentication, troubleshooting OSPF. We got several different discoveries that we'll be doing today for that as well. All right, so this is our device information. Again, keep in mind for the Ethernet interfaces, the first digit is always going to be a 1. The serial interfaces are always going to be 20, so just keep that in mind. All right, so the first thing they want us to do is they want us to go into router 4, and we're going to be looking at the intra-area prefix LSAs. Intra-area prefix LSAs. So what are we talking about in this particular case? What is an intra-area prefix LSA? Wouldn't that be considered a type 1? LSAs that exist within the area. And they represent the prefixes within the area. So we'll take a look at that. Let's go to router 4 first and investigate the routing table. Make sure that we have full convergence here. We should see several OIA routes. All right, so if I do a show IP route, show OSPF v3 route, sorry, show IP OSPF, show IP route OSPF v3. We'll get there eventually. All right. So as suspected, we do see several different types of routes. Here's that external route. Remember, it comes in as an OE2. Later on today, we'll talk about what the difference is between OE2 and OE1 and how we can modify that actually during the redistribution process. But this is an external route, so that's going to be representative of a type 5 LSA. Type 7 would be an N. Remember, N stands for NSSA. So N is an external route coming from a special area type. E1 and E2, those are going to be my type 5 LSAs. OIA, those are my inter-area routes, my type 3s. So it makes sense we see quite a few type 3s on router 4 because if you look at the topology, We've got this WAN link here. We've got this loop back here. We've got this WAN link here. We've got loop back on router 3. All of those should be coming in as inter-area routes. And we do see that there's a bunch here, 16, 17, 18, 19, 20, 21, 22, 23. Those are going to be coming from probably router 2, if I remember correctly. I think we have a bunch of sub-interfaces, not sub-interfaces, but secondary IPs on router 2. Let me take a look real quick. Show run interface, loopback 0. Yeah, so we've got all these different secondary IP addresses on this interface. Again, not something you would typically do in the real world, but the idea here is that we're generating additional prefixes. Later on, we're going to be taking a look at how do we summarize these routes on our ABR, right, using the area range command. So that's probably why we've generated so many prefixes. But these are all coming in as OIA routes. All right. They actually did a show IP route. I did a show IP route OSPF v3. The only difference is we're just taking away those connected and local routes in the output here. All right. And actually, it looks like they might be missing a few. Well, they did that on router 4. Let me take a look real quick. If I just did a show IP route, if it's going to be similar. Yeah, they're missing all these loopbacks here. They did have the 2.0, but that's okay. We've got these other loopbacks. We're just generating some additional routes in our output here. All right. Show IPv6 route. If we look at our show IPv6 route, again, you can do a show IP route. Show IPv6 route. There isn't an option to do an OSPF v3 here, but we can certainly do OSPF to look at just the OSPF routes. We see the 12, that's the WAN link between router 1 and router 2. The 13 is the WAN link between router 1 and router 3. The 22, that's the loopback on router 2. And then this is the external network that comes from router 3 being the ASBR. Now notice it's slightly different, right? We don't see the IA, but the I is inter-area routes, and the E2 is external type 2. Now the 2 doesn't mean that it's an external LSA type 2. External type 1 and type 2, which we'll talk about in more detail later on, is representative of how the metric is going to be applied to the route that's coming from that area. That's the point of the 2 and the 1. And I'm not going to talk about that right now because we're going to have a discussion about that a little bit later on. But it has to do specifically with how the metric is evaluated based on the seed metric, and then how that metric changes or doesn't change as it propagates through the OSPF domain. All right. So we see that E2 route here. We see the 2 OIA routes. So it looks like our V6 output is pretty accurate. From the routing tables of R4, we see several routes because the routers in the lab are pre-configured. We have some intra-area routes. 1.0 is an intra-area route. We see that one right here, actually. Should be an O route. Intra-area, meaning inside the OSPF domain. That intra-area route is the loopback on router 1, which is in area 0. So this is a type 1 route. These are type 3s. These are type 5s. All right? So we see that intra-area route. We see all the inter-area routes, which are the WAN links. And then we have this 2.0 remote subnet. So it looks like their intention was not to have those other prefixes in there, but that's okay. We'll just leave them in there. It's not going to bother us too much. All right? Same thing with IPv6. Our intra-area route would be 11, and we see that in the database as well. Right here is the DB8011. That's our intra-area prefix. Again, the loopback coming from router 1. And then we have the WAN links, and we have the loopback on router 2, which is coming from a different area. All right? You'll also notice, by the way, you'll see if I just did a show IPv6 route, you'll see this null zero route for multicast. We don't actually see that in the V4 routing table. We see it in the V6 routing table, but that is not a function of OSPF. That is a function of the link local multicast, not link local, but the multicast traffic that's going to be generated by the multicast. If I do a show IPv6 interface Ethernet 1.0, for example, you'll see that even if I wasn't running OSPF, these two particular multicast addresses are for OSPF, but this is an all routers multicast group, this is an all host multicast group, and these are multicast addresses that are used for duplicate address detection. So the router's participating in a bunch of different multicast groups, and this null zero route is kind of like a summary, and it provides that loop avoidance mechanism for multicast traffic, so that I'm not forwarding multicast traffic or sending multicast traffic outside of the router that doesn't, it's not supposed to go there. All right. All right. They didn't mention that in the book, but there's also routing information about the external route. That's the 10.0/16 route or the 10.10/64. That's being redistributed from router 3. If I were to go to router 3 and take a look at that configuration real quick, we would see under the routing process that we actually have a redistribution process taking place. All right. Right here, redistribute static into our V4 unicast address family and redistribute static into our IPv6 unicast address family. And if I do a show run pipe include IP route, we can see that 10.0/16 route, and if I do a show IPv6 route, we can see the IPv6 10.10:/64 route. So those are the only two static routes that exist on this router, but they're being redistributed into OSPF. And that's actually kind of an important point, right? We don't actually define that router 3 is an ASBR. The fact that we're doing redistribution is what makes it an ASBR. All right? So it's originating those type 5 LSAs because we're doing the redistribution. And it doesn't have to be redistribution from another routing process. In this case, we're not redistributing from another routing process. We're actually redistributing from static routes that are locally configured. So any redistribution will generate those type 5 LSAs, not just redistributing from another routing process or routing domain. What I mean to say is not from, say, EIGRP or BGP or whatever. All right. OSPF v3 uses the term link for what OSPF v2 calls a network. All right. And that makes sense, right? Network LSAs versus link LSAs. OSPF v2 expresses network LSAs with their address and mask. OSPF v3 expresses network LSAs as a prefix and prefix length. And generally speaking, that's usually how we define what a network is anyway. Prefix is the network ID. Prefix length is the subnet mask. So you'll hear me use that term a lot, actually, as I'm going through different lessons. I'll just say, what's the prefix length of that particular network, or what is the network prefix that we're trying to advertise? Those are synonymous terms to address and subnet mask. But again, it's defined that way in the database. So let's go back to router 4, and we're going to look at a summary of the database to start with. We're not going to look at the whole database. We're actually going to take a look at the summary of the database. So we're going to do a show IP OSPF v3, or show OSPF v3 database. All right. Make sure that's what they want us to look at here. Actually, yeah, they just want us to look at the v4 for right now. So let's do that. IPv4. And we'll look at the v6 in a little bit. So as you break down this database, remember, this is not a detailed list of the database. Basically, what you're looking at here is a summary of the database. And then if you wanted to drill down into each component of the database, which we're going to be doing throughout the lecture, throughout this particular discovery, you can see the details of each of the entries. So this is our V4 database. Had I left out the V4, we pretty much would have seen the same thing. It's just we would have seen it, the V4, and then we would have seen the V6 after that. So it doesn't matter if you decided to use the V4 or not, but router link states, those are my type 1 LSAs. So I know that based on the fact that I ran this on router 4 is in area 0, it's only going to get type 1 LSAs from other routers in the area. So we know that router 1 is in area 0 because router 4 is in area 0, and these are type 1 LSAs. All right? Notice you don't really see anything about prefix information. You don't see network IDs, you don't see subnet masks, you don't see cost. Remember, this is the topology database or the global RIB for OSPF, and you would expect to see actual routing information. Well, you will. If we were to drill down into each of these sections, which we will do later on, you'll see that information as part of the discussion. The netlink state LSAs, these are my type 2 LSAs. Who generates type 2s? The DR. The DR for that segment. So we know based on the fact that router 1, the router ID for router 1 is listed as the advertising router, I know that router 1 is the DR for that particular broadcast domain. And by the way, there's 2 routers attached to that multi-access network. Does that make sense? All right. And again, we'll talk more about like the sequence number and the age. I could tell you about the sequence number right now. This is always going to be the initial sequence number of your LSAs, the hex 8000000001. As the router receives updates for those particular advertisements, it increments the sequence number. So in this particular case, none of these particular LSAs have been updated since they were originally learned. These 2 LSAs were updated. So if I was to, for example, go into router 4, show IP interface brief, and I was to shut down Ethernet 1.0 and do a no shut, and then I was to go back and look at the database, I would see that those LSA numbers would increment. All right? Because again, I'm relearning information about that particular prefix or that particular network. All right? Especially router 4 is originating that. And by the way, that was a point-to-point link between router 1 and router 4. So shutting down the router 4 side ended up shutting down the router 1 side, which means we had triggered update from router 1 as well. So what do you suppose the inter-area prefix LSAs are? In classic OSPF, these would have simply been called summary LSAs. Inter-area gives it away though, doesn't it? Inter-area means type 3s, prefixes that are coming from another area. Notice who the advertising router is for every single one of these. The advertising router is router 1, which tells me that router 1 is an ABR. Right? Router 1 is an ABR. The sequence number tells me that I haven't received any updates about those prefixes. But if I was to go into router 2, for example, and go into interface loopback 0 and shut that down, and then do a no shut, and I go back to router 4, I should see the sequence or those particular LSAs increment, meaning that I just got a new advertisement for these particular prefixes. These are all the prefixes that are tied to loopback 0 on that router. Right? So you can always tell based on the sequence number how many actual LSAs or link state updates I've received for those particular prefixes. So, and these are, of course, all the different prefixes with the prefix length for each of the subnets. These would be the ones that I would want to summarize. Right? That's why we have the 16, the 17, the 18, all the way up to the 23, because later on we're going to do a summary to summarize those into the rest of the areas. All right? This one here, inter-area router link states, this would have been previously called in classic mode an ASB summary, or an ASB summary LSA, which, by the way, represents what? What type of LSA is this? It's not a 1, 2, or 3, because we already did those, so what must it be? What do you think most likely it is? Look at the destination router ID. It's a type 4. It's a type 4 LSA that describes the ASBR. Remember, the ASBR in our topology is router 3. The advertising router is the ABR. The ABR is the router, is the ABR that's attached to the area that has the ASBR in it. So this is actually a type 4 LSA. All right. Then we have our type 8s and type 9s. This is my type 8. It's kind of funny that they actually put type 8. It would be kind of nice if they would just put the type on all of them, right? Why not, right? Why not just tell you what all the types are? But the type 8 LSAs, we'll drill down into those later on as well. But these would be representative of my link local addresses, the FE80 addresses. And we'll drill down into that later on. The intra-area prefix LSAs, we'll see this in detail a little bit later on as well. These are my type 9 LSAs. And then finally, we have our type 5. So these are the only two LSA types that are related to IPv6. We wouldn't see type 8s and type 9s for IPv4. But it's kind of interesting because when we ran our command, we said, show me the v4 database. Why the type 8s and type 9s show up in the v4 database, I have no idea. It certainly has to do with the fact that we're running OSPF v3. If we were running classic mode, we would not see these LSA types in the v4 database. We would only see these LSA types in the v6 database. So because we're running OSPF v3, we're probably using v6 as our transport to carry v4 information. We have to have these v6 LSAs in the v4 database. All right? And then our type 5, look at who the advertising router is of our type 5 LSA. The advertising router is router 3, and this is representing the external prefix. So the type 5 LSA is originated by router 3, which then allows us to identify the external networks that are being redistributed into OSPF. All right, I'm not sure that the book get into that much detail. I don't think they break it down that much. We will actually break down each one, but if we look at the v6 database, it's actually going to look pretty much the same, right? There's your type 1s, there's your type 2s, there's your type 3s. We don't have as many type 3s in this case. Inter-area, again, renamed from summary LSAs to inter-area prefix LSAs, right? Another set of inter-area, well, this is my type 4, right? Again, I can recognize, and this is very, very confusing. If you look at this quickly, it looks like these are the same, right? But this is an inter-area prefix link state. This is an inter-area router link state. So make sure you pay attention to that. If you see something like that on the test, maybe they're going to ask you who the ASBR is in the topology. That's kind of common, actually. They'll give you an output like this, and they'll ask you questions about the topology, and you have to be able to recognize, based on this output, what the role of a particular router is, right? I can see from this inter-area router link state LSA that router 3 is a ASBR, because I happen to know that this is a type 4 LSA. Type 8 and Type 9, of course, again, and our external Type 5s, but in this case, representing an IPv6 destination, not an IPv4 destination. Does that make sense? All right. All right. The OSPF v3 database contains all the LSAs that describe the entire network topology. We can use the command that we just did, the show OSPF v4 v6 database command, to verify it. The output reveals the presence of different LSA types. For each LSA type, you can see which router advertised it, the age of the LSA, and the link ID. Based on who's advertising it and the link ID, it really depends, right? Certain LSA types, the link IDs represent the router ID of the generating router, or the link ID might represent a prefix. For example, if you look here, you can see this. I'm trying to see if we'll have to drill down actually. But for example, if I was to look at the v4 database and specifically look at the router LSAs, link state ID is what they're referencing here, right? The advertising router, link state ID is what they're referencing here. So we'll drill down into these and take a look at the details in a little bit. In the output, you can see two different router LSAs generated by the routers with router ID 1 and 4 respectively. We will verify the details of those two LSAs, which are the router LSAs. All right. Remember, type 1 LSAs are intra-area. They're generated by everybody within the area, and they describe the links that are directly attached to you. Okay? So based on our topology diagram, I would expect router 4 to generate one type 1 LSA that includes information about the 14 subnet. I would expect router 4 or router 1 to generate two type 1 LSAs within the LSU, right? Because you've got the 14 subnet and you've got the 1.0 loopback. That's what we would expect to see in that case. All right? These type 1 LSAs flood in the area only. They do not cross the ABR. They are identified by the router ID of the originating router. We actually saw that in the output, right? The advertising router is the router ID of the router that's originating the type 1 LSA. No prefix information. We'll take a look at it and see what we see. So if you want to drill down into the database, you're going to use the command to drill down into each LSA. For example, if I come in here, try that again, and I do a question mark, these are all the different details that I can see. I can look at advertising router information. I can look at a summary of the database. I can look at my external LSAs, my inter-area prefix LSAs, my internal LSAs, my network LSAs. It's a little bit challenging with these because with these outputs because the names here don't directly reflect the names in the database. So you kind of have to interpret what they're saying. Usually the description is probably a better thing to look at, right? These are my inter-area LSAs. These are my link states, which are essentially my my type 8s. My NSSA external would be my type 7s. External would be my type 5s. So you kind of have to play around with it a little bit to get used to the database and how to parse the database. One thing that I also like to look at is the self-originate, because that will tell you what you're originating into the OSPF autonomous system. Self-originate are all the LSAs that you're generating. So router 4 is generating type 1s and type 8s. Make sense? Now, if I want to drill down into the database itself, let's say, for example, the type 1s, I'm going to use the router LSA. All right? The router keyword, excuse me. So now you're actually going to see within the area, because again, all the routers in the same area have the exact same database. That is, by definition, that has to be the case with OSPF. Every router within the area has to have a duplicate database. When we're fully converged, that would be the case. So technically, you could run this command on any router in the area, and you should see the same information. Okay? What's important about this is this right here. We may be able to receive information about a prefix, and we might be able to identify that routing information exists, but for some reason we may not be able to route to that destination. When the routing bit is set, that means not only do we learn about that destination, we're able to route to that destination. Because again, OSPF is about routing to nodes, it's not about routing to networks. So if for some reason the node wasn't reachable, that routing bit would not be set. All right? All right. So we see here the advertising router is 1.1.1.1. We've had 3 different updates to this particular entry. All right. Router 1 happens to be an ABR. Again, that's not relevant to the router link states, but we know that router 1 is an ABR because it's advertising itself as an ABR. All right. How many links is router 1 advertising? 1 link in this particular LSA. We don't see the actual information, but we will see the information in another type of LSA. That's another thing to think about here. We don't see any prefix information here. All right, and here's the reason why, because they're carried in the type 9s. In OSPF v3, they're going to be carried in the type 9s. So when we go back later on and analyze the type 9s. Now, if this was classic OSPF, if we were running just standard OSPF, you would see the prefix information in the router LSA because you don't have type 9s for IPv4 in classic OSPF. But because we're running OSPF v3, that link information, the specific details of the link information is going to be carried in the type 9s, which we'll see a little bit later on. All right, we do see the metric for the link itself, cost of 10. It's Ethernet, so it would have a cost of 10. The DR is router 1, and I'm router 4. I'm running this on router 4. So that's that LSA, and then I see one for router 4. All right, number of links 1. It's connected to the transit network. This is the DR for the transit network. So again, if I do a show IP OSPF database, show IP, let me keep forgetting I'm running OSPF v3. Show OSPF, show IP OSPF, show OSPF v3 IPv4 database, right? These type 9s, the intra-area prefix link states, that's where we're seeing the actual information, the details. All right? So how would I see those intra-area prefix LSAs based on this output? Which one do you think I'm going to choose here? Remember, it's intra, not inter. So is it internal or is it linked? That's what I was saying about how it's a little confusing because there's not a direct correlation with the command versus the actual output of the database. It'd be nice if they just listed it as an intra-area prefix LSA. So it's either internal or link, right? But my guess is that the link LSAs are going to be the type 8s, because it does actually say link there, the link states, which are the type 8s. And this is link state, so that's the type 8. So it's probably going to be this one right here, internal LSAs. So if I do internal, show, here, let me do this. Internal. There we go. All right. Well, that doesn't give me the information that I want, so that can't be the right output because it just gave me the database. So again, we have to kind of find the right command to look at those specific LSAs. So let's see. Network is type 2, prefix link states. That could be it actually, because that would, yep, it's the prefix ones. So this is where these are the type 9s, right? Again, we're seeing the same information. The advertising router is router 1, but now we're also seeing the actual network prefix, right? This is the 1.0 loopback. It's got a 24-bit mask. This is probably the 14. Yep, this is the 14, and it has a 30-bit mask. So these type 9 LSAs represent the actual prefix information, and the type 9 LSAs are associated to the type 1 LSAs. Does that make sense? If this was classic OSPF, OSPF v2, we wouldn't even have these type 9s, and this information, this prefix information, would be represented in the type 1. All right? So if you look at the router, you can see here the information is similar, right? The sequence number is 4. The advertising router, the advertising router is 4, or the advertising router is 1. And then we also have the metric is listed here, but the metric is not necessarily listed in this output here, right? It says metric of 0. That's not the metric for the network, right? Because this is the originating router, so it has a metric of 0. Now this one has a metric of 1, indicating that that's a loopback. But the idea is that you cannot just look at the database. Like if you look at an EIGRP topology database, it's very simple. Successors, feasible successors, routes that don't qualify. With OSPF, it's very complicated because you have different LSA types that represent different types of information. And oftentimes you have to look at multiple LSA types to infer what's actually happening in the topology. Does that make sense? When I do this in my CCIE class, we go into this in even more detail, and we really break down the relationship between the different LSAs. So they weren't having us look at the prefix LSAs in this case, but the router LSAs, they're generated by every router. They're flooded within the area. They describe the state of the router link states, or the router links in that particular area. R4 has 2 router LSAs in the database, one received from R1 and one that it was generated by R4. All right, we saw that in the list. Notice that the prefix information is not included in the router LSA as it is in OSPF v2. So they're repeating what I was telling you before. If this was classic OSPF, I would actually see the prefix information, the network ID, the subnet mask, in the router LSA itself. The OSPF v3 router LSAs only describe who's generating that information so that we can identify how we're going to build our tree and how we're going to do our shortest path calculation. The prefix information is carried in the type 9s. The type 9s are the intra-area prefix LSAs. All right? So it's a scaling function, as they mentioned here. It's an important improvement in scaling the protocol. OSPF v3 removes the prefix advertisement function from the router LSAs. Now router LSAs only represent the router's node information. Again, I said this multiple times, it's all about the nodes, it's not about the networks, right? And they're flooded the information, and that is pertinent to us being able to calculate the shortest path tree. If a prefix changes or the state of a stub link changes, that information is only flooded based on the type 9s, not based on the type 1s. All right? And it doesn't actually trigger a calculation. That's probably a little bit more detail than you actually need to know for the scope of this class, but that was the reasoning behind generating those type 9 LSAs, was to make the protocol more efficient. All right? The link state database, that's going to be where we're going to hold or house all of our link state advertisements. Local LSAs, we'll talk about as part of this as well. In fact, they mention it right here. I already showed you that. Self-originate would be any LSAs that you are generating yourself. All right? And that can be useful for troubleshooting because you're trying to maybe identify whether or not you're originating a particular prefix or you're generating a specific type of LSA. Maybe you're trying to identify what type of router that is. If it's a DR for a particular segment, if it's an ABR connected to an area that has an ASBR in it, maybe it's generating a type 4 or type 5 if it's an ASBR. So self-originate will give you the ability to identify whether or not, or to identify specifically which LSAs you're actually generating yourself. All right, we actually did that already on router 4, and we can see that we're basically just generating. Well, we should actually have more. Oh, in this case, they're not. We just did the V4. Before I just did self-originate, not router self-originate. So self-originate shows me not only the type 1s that I'm generating, but also the type 8s. Again, we wouldn't see this in OSPF v2. We're applying the v4 argument to the command, right? Show OSPF v3 database, but the v4 database specifically. It's a little confusing because you're seeing type 8s, which are v6 specific LSAs, but again, that happens to be because we're running OSPF v3. And IPv6 is the transport for our OSPF information. So it always has to exist in the outputs there. All right. Show OSPF v3 IPv4 database prefix internal. So what are we looking at in this particular output? Copy that. This is we're doing this on router 4 as well. So again, look at the command. Prefix internal means what? Prefix are the type 9s. Internal is what? Intra-area, right? So we're looking at, if we look specifically at the LSA types, intra-area prefix LSAs, so this is the 1.0. This is actually being generated by router 1. So this is the loopback on router 1. And then we see the 14.0 subnet that's also being generated by router 1. So these again are my type 1 LSAs. Well, actually they're my type 9s. Router would be my type 1, but they do represent internal networks, the link information, the specific details of the link information. All right. R4 is receiving 2 intra-area prefix LSAs from in area 0. The first LSA describes the prefix for router 1's loopback, which is 1.0/24. The second is the shared link between the two routers, which is the 14 subnet. A similar output would be available in the IPv6 address family as well. Show OSPF v3 IPv6 database prefix internal. Now let's take a look at the database on router 2. The database on router 2 should be different, slightly different. Again, the databases within the area are going to be identical. Router 1, router 4, they're going to have an identical database. Router 2 is in a different area. So router 2, most likely we shouldn't see any net link information. We shouldn't see any type 2s. We should only see type 1s, we should see type 3s, we should see type 4s, we should see type 5s, we should see type 8s and type 9s. All right, so if I go to router 2, and there's my type 1s, here's my type 3s, so again, no type 2s, because it's a point-to-point serial link. There is no DR, BDR election on a point-to-point serial link. I see my type 4 right here, ASB or router, right? Destination router ID is router 3. My type 8s There's my type 9s right here, and my type 5s, which represent the external network. All right. OSPF v3 router LSAs are exchanged only within the OSPF areas. Router 2, which has interfaces that are configured in Area 1, should not see any router LSAs that were originated in Area 0. Makes sense, because router LSAs are specific to the area. The output of the database confirms this condition. No router LSAs are being received by router 4. We actually do see router LSAs from router 1. Oops, let me go back up. That's not my router LSAs. I do see router LSAs from router 1, but because router 1 is the ABR, it's participating in the area. Router 1 is going to have type 1 LSAs in all of the areas. All right, so router 1 really would be the place to start doing any kind of major troubleshooting, because it really should have the most complete database because it's participating in all the different areas. So if I go to router 1, take a look at the database on router 1. I'm going to close this one here. Take a look at the database on router 1. You'll notice how the database is actually organized. It's organized by area. So you see all of the LSAs for Area 0, then you see all of the LSAs for Area 1, and then you see all the LSAs for Area 2. So it doesn't group them by LSA type, it groups them by area. But you can see we have quite an extensive database in this particular router because it is participating in all the areas. Here's my type 1s for Area 1. Here's my type 1s for Area 0. Down here are my type 1s for Area 2. I've got type 2s for Area 2. Router 3 is the DR for Area 2. Remember, type 2s are netlink states, so router 3 is the DR for Area 2. Who's the DR for Area 1? We don't have one. There's my type 1s, there's my type 3s. There are no type 2s. We already determined that on router 2 anyway, right? And then for Area 0, the DR is router 1. Make sense? All right. So router 1 is really going to have the most detailed information in the database. Router 1 is the only router that lies in multiple areas. Because it's an ABR, its database includes router LSAs and intra-area prefix LSAs, type 9s from all 3 areas. Now we're going to take a look at a deep dive into the network LSAs. Remember I described this the other day. I said network LSAs don't really describe prefixes. You will see some prefix information, but the purpose of a network LSA is to describe a transit network or a broadcast domain, right? It includes a list of all the routers that are attached to that broadcast domain. It includes the subnet mask of the broadcast domain. It is advertised by the DR of that particular broadcast domain, and it's an intra-area LSA, which means it does not go beyond an ABR. All right? It says one network LSA for each transit broadcast network or NBMA. We've seen this term quite a bit, right? NBMA? Non-broadcast multi-access is what that stands for. Frame relay, X25, ATM, these are all examples of non-broadcast multi-access networks. Multi-access meaning that you can have multiple devices sharing a common broadcast domain. Non-broadcast mean that the transport, the data link layer transport doesn't support the transmission of broadcast traffic. Traditionally in the past, frame relay, ATM, those protocols were configured to disallow broadcast traffic over the transport because they were very slow. We didn't want to have our network overwhelmed with a bunch of broadcast traffic, right? It's not that frame relay doesn't actually support broadcasting, it does. You can actually build your PVCs to support broadcast traffic, but service providers would basically prevent that from happening for efficiency purposes. All right, a network LSA is generated for every transit or NBMA network. The DR of the network is the one that advertises the network LSA, and it basically just describes, like I said, who's attached to that broadcast domain. Because again, the DR is the one that's responsible for managing the database for those attached routers. So if something changes in the network, we have to notify the DR. The DR is then responsible for notifying the other routers in that network. So it's important that we know about these networks. It's important that we know who is managing this network, right? So let's take a look. They want us to do this on router 4. Yeah. So they want us to go ahead and run this command here, show OSPF v3 IPv4 database. Again, this is just the summary of the database on router 4. And what they want us to see in this case, let me go to the right router here, is just to see if we have any type 2 LSAs, right? And we do, right here, netlink states. Now, if I was to use the question mark, which one of these outputs would allow me to drill down into those netlink states? This one's actually pretty easy to see. Network, right? And look what we see here. Notice there is no routing bit because, again, we're not really describing destination prefixes. We're simply describing the network that the DR is responsible for. These are the routers that are attached to the multi-access network. This is the advertising router, which means that it is the DR because it's the only router that's going to be generating the type 2 LSA. But you see, we don't really see any prefix information. In fact, there's nothing here about that prefix information. That's going to be carried in our type 9s. Type 1s to describe the links, type 9s to describe the prefixes. So really all we're just saying is who are the nodes that are attached to this multi-access network and who's responsible for that multi-access network, okay? Notice how router 4 only has one network LSA in its link state database. This condition is expected because there's only one multi-access network in area 0. That's actually a pretty good point because you could have multiple netlink states in your database if you have multiple DRs. Every single DR is going to generate type 2 LSAs. If I had this link between these two routers and then maybe router 4 had another multi-access network connection to different routers, then we would see multiple netlink states. But again, these are only flooded within the area. They're not flooded outside of the area. All right. So they did they drilled down as well the network LSAs, and again we see in their case router 4 was the originating router. In our case, router 1, in my case, your case might be different depending on how your router's booted up. Remember, once the DR is elected, you stay the DR. Router 4 technically should be the DR if you were looking at the algorithm because it has a higher router ID than router 1. But in my case, as I booted up my routers, it seems like router 1 came online before router 4 did, so it became the DR. All right. It doesn't actually really matter. The only difference in the output is the advertising router because we still have the same attached networks or the same attached devices. All right. The content displayed in the network LSA describes the network link listing the DR router ID, right? The advertising router is the DR's router ID, and all of the attached routers. This information is used by each router participating in OSPF to build a picture of that multi-access segment, but that cannot be described with just router LSAs. And again, this goes back to what I've been mentioning multiple times, is that you cannot look at the database individually. You can't look at netlink states and see what's happening. You can't look at router LSAs and see what's happening. You can't look at prefix LSAs and see what's happening, or inter-area or intra-area prefix LSAs or whatever, whichever one you decide. You have to look at the database as a whole because a lot of these LSA types are related to each other. What are we investigating now in this particular case? Inter-area prefix LSAs, which are which type? Inter, not intra. Intra-area prefix LSAs are type 9s. Inter, meaning from one area to the other, 3s, right? Type 3s. ABRs, right? Generate these. They don't forward the router or the network LSAs, but we still need to learn about how to reach those other networks. And this is where the type 3s come into play. Type 3s are used to flood network information to areas outside of the originating area. They describe the network number and the mask, basically the prefix information. Advertised by the ABRs, they're actually technically summary LSAs, but we know that summarization doesn't occur by default. So if I have 1,000 type 1s in area 10, and I don't have an area range command on the ABR, I'm going to have 1,000 type 3s in area 0. All right? So for every basically router LSA and intra-area prefix LSA, I'm going to have some sort of representative inter-area prefix LSA or type 3 LSA. Advertised for every subnet not summarized by default. The ABRs generate these inter-area prefix LSAs to describe networks that are owned by an area to the rest of the areas in the autonomous system. They are flooded throughout the single area only, but are regenerated by the ABRs and flooded into other areas. Notice that the diagram only illustrates how information is propagated from area 10 to the other areas. But what they're saying here is basically, look, yeah, they're going one way, but they're also going the other way. Right? Area 20 prefixes are going to come into area 0 as type 3s. Area 0 prefixes are going to go into area 10 and 20 as type 3s, and so on. As a best practice, we use manual route summarization on our ABR to limit the amount of information that's exchanged between the areas. All right, so let's go back to router 4 and look at our database again. Right? And sure enough, we see our inter-area prefix LSAs, which are all of these prefixes. Now, this is not part of the exercise, but what if I wanted to summarize 16, 17, all the way up to 23? What would first of all, what would the summary be? 16, 17, 18, 19, 20, 21, 22, 23. That's 8 networks, right? So it's a block of 8. Is 16 divisible by 8? Yes. So I can actually summarize these prefixes in one nice, concise block of 8. Which octet would I be summarizing in? Third? I'd be summarizing in the third octet, which would be a 248, right, in the third octet. If you guys recall how I do that summary, first of all, I can only do the summary on the ABR, which would be router 1. So I can come into router 1 here, and I can say, okay, config T, router OSPF v3, I think it's 1. Let me do a quick show IP protocols. 1, yeah. And I'm going to go into my address family for IPv4 unicast because I'm summarizing v4. I'm not summarizing v6, right? Area range, and where are these prefixes coming from? The prefixes are coming from area 1. When you use the area range command, it's always the area that the addresses are coming from, not the area that you're sending the summary to. That makes sense? So I'm summarizing prefixes from area 1, 192.168.16.0, 255, 255, 248.0. Okay? We did that before in the Encore class. We'll probably do it again in a future lesson today, but again, I just wanted to demonstrate these 16 subnets weren't even in the original discovery anyway. So if I now do show IP OSPF, show OSPF v3 database self-originate, you can see that I am now generating that summary. I'm no longer seeing those individual prefixes. I'm generating the summary. Which means now on router 4, I should see the /21 as well, instead of those individual 16, 17, 18, 19, 20. All right? From router 4's perspective, it doesn't look any different. Router 4 doesn't know if that's an actual summary. That might actually just be a route that exists on router 2. There's nothing to say that this is truly a summary, that the area range command was used. Doesn't matter. It's represented as a type 3, which means technically it is a summary LSA, but it doesn't necessarily mean that it is a summary. You see what I'm saying? If I was to drill down, because that's what we're going to do next, you'll see that it looks just like the 2.0 in the database. All right? So we'll use this command here, intra-area prefix. You actually don't even need the prefix keyword, but we'll put it on there. And here's the 12.0 subnet with a /30. So that's my point, right? That is actually not a summary. That's the actual prefix information from the link between router 1 and router 2. That's the WAN link between router 1 and router 2. Notice we do see the metric here, 64. We haven't talked about the cost or metric for OSPF. We'll be doing that a little bit later today as well. It just happens to be, actually this is somewhat important because I'm on router 4. This is a very interesting concept. I'm on router 4 and it says the metric for that prefix for that network is 64. If I do the math though, if I'm looking at the topology diagram, yes, that's a WAN link, right? So to calculate that metric, we use the formula 10 to the power of 8, which is the default reference bandwidth in OSPF, divided by the link speed in bits per second, 1544000, because it's 1.544 megabits per second. There's the 64. Remember, we just dropped the remainder. But that's interesting because router 4 is over here. And it's saying the metric for that link is 64. So that is not the metric to reach that network. That is the metric from R1's perspective. Because R1 is the one that's generating the prefix. If I want to see the total path cost to get to the 12 subnet, I have to use my type 1 LSA and my type 9 LSA to identify how I get to router 1. Then I can add that on top of the cost that's being included for the type 3, and that gives me my total path cost. That's why I keep saying it's about routing to nodes, not routing to networks. Basically, router 4 is saying, okay, you're the advertising router, you're the ABR. I know that once I get to you, it costs me 64 to get to this network. I use a different LSA type to determine my cost to get to the ABR. Does that make sense? All right. Let's see, what else? We should see some other ones here. There's the 16 with the /21. That has a cost of 65, which makes sense because that 16 represents the loopbacks on the router. And from the ABR's perspective, it costs 64 plus 1, because if you look at the bandwidth of the loopback, it's faster than 100 meg, so it's always going to have a cost of 1. Remember that reference bandwidth is a bit of a problem in OSPF because
anything that's fast Ethernet and above is going to have the same cost. The bandwidth of a loopback is like 800 megabits per second, I think, something like that. We can actually see that show interface loopback 0. Let's see, yeah. I think that's 800 meg. Yeah. All right. Because that's 8 million kilobits per second, not 8 million bits per second. All right. So again, completely different concept than say EIGRP, where we can just look at the topology database and figure out how routing is occurring. In this output, we don't have that option. Right? We should have also seen the 2. Yeah, here's the 2/24. All right? And that has a cost of 65 as well, once I get to the ABR. All right? If I looked at the router, notice the router doesn't really give me any metric information. So I would actually have to look at the prefix. And this is where I can see, okay, the cost to get to router 1, let me find the right one, 14. The cost here, it should be listed, so the metric here is listed as 0, but let me see here, maybe under router, right here, link metric, that's what I was looking for. So this is what allows me to identify the node in the domain. And notice here it does say this is the ABR. This is the cost to get to the ABR. So that would be the cost that would be added to the cost of the type 3 LSA to indicate the total path cost to get to those destination prefixes. All right. There is detailed information about 3 v4 networks. We actually have more than that, but each LSA has a link state ID field which serves to differentiate multiple LSAs originated by the same router. The prefix address and the length are also displayed. That's what we're saying here. Here's the prefix, here's the length. Prefix length is the subnet mask, prefix address is the network ID, and the advertising router is the ABR. Prefix address and length are also displayed. You can also see that all 3 LSAs were advertised by the router with the router ID of 1.1.1.1, which is the ABR. All right, next task, inter-area router LSAs, which are type, key is the router, keyword here is router. They ain't type 1s, 2s, or 3s. Would you guess maybe potentially 4? Yes, they're type 4s, right? You can see it actually right here in the diagram. Remember, if I have an ASBR attached to an area, the ABR is going to advertise type 4s. And what was the purpose of a type 4? Notice that it is inter-area. Type 4s will never go into a special area type. They will never go into a stub, totally stubby, not so stubby, or totally not so stubby, but they will get propagated to all other areas. All right. Used to advertise the metric of the ASBR, or the metric to the ASBR, which allows us to do path selection. It has nothing to do with the actual external prefixes. The type 5s are what the external prefixes are. How did this ASBR notify the ABR that it was an ASBR? If you actually look at the packet captures for the hellos, there's a bunch of flags that can be marked in those packets and also in the updates that are sent. And when we're generating our type 1 LSAs, we generate the type 1 LSAs with an external bit set indicating that we are an ASBR, meaning that we're telling everybody in the area that we're generating type 5s. Or type 7s if it's a special area type. All right. The router ID of the ASBR. So again, type 4 LSAs
are about node reachability, not about prefix reachability. So we're not advertising any prefix information. An inter-area router LSA is generated by the ABR only when an ASBR exists. So you'll never see type 4s without type 5s or type 4s without type 7s. Type 4s will work with both type 4s and type 5s and type 7s. An inter-area router LSA identifies the ASBR and provides reachability to the ASBR. Obviously, we're going to drill down and take a look at that. All right. So again, going into our database, we're just basically looking at our database on router 4 to see if we see any type 4s. And sure enough, we do see type 4s right here. The inter-area router link states. Now, what command would I use to see those or to drill down into the type 4? Could it be this inter-area here? See, this is where, again, it's a little confusing because they use the term inter-area here. So you might say, well, okay, this is inter-area. Is it router? No, those should probably be type 1s. Right? Which one do you think it is? Could it be inter-area? Let's take a look. Oops. Inter-area. So we have the option of looking at our type 9s, or we have the option of looking at our type 4s. So we're going to look at our type 4s. All right. Routing bit set means that we have reachability to the ASBR from router 4. The advertising router is not the ASBR. The advertising router is the ABR. But it's interesting because it says the metric is 10, which is very interesting because that is not the overall path metric. That is the metric for the ABR to reach the ASBR. So if I had multiple ABRs in this area, maybe one has an Ethernet link, maybe one has a serial link to the ABR, maybe one has different paths, we're going to choose to go to the ABR that has the best path cost to the ASBR. So this 10 represents essentially the cost for this ABR to get to the ASBR. We already know how to get to the ABR from our type 1s. And we know what the cost is to get to the ABR from our type 1s. That's where we saw that link cost to get to the ABR. So this is just the cost for the ABR to get to the ASBR. Notice we're not seeing any information about the actual prefixes that are being generated by the ASBR. The external prefixes. All right. There's only one inter-area router LSA. It was generated by the ABR and it describes the ASBR. Again, inter-area, we would have to choose prefix or router. In our case, we chose router because we're looking at the type 4s, and that's what we see. All right. Next is our type 5, which is our external LSAs. These are pretty much very simple to understand. They simply represent the networks that are being redistributed. Notice that they are inter-area, meaning that they move throughout the domain. You will never see type 5s in a special area. Type 5s are not allowed into a special area. Special area meaning stub, totally stubby, not so stubby, totally not so stubby. You'll never see a type 5. You might see type 7s if it's an NSSA or totally NSSA, but you won't see type 5s. Used to advertise networks from other autonomous systems. That's a little bit misleading, right? Because technically, redistributing static routes isn't really another autonomous system. Redistributing connected routes is not really another autonomous system. When somebody sees this, they think, well, it's routes from EIGRP or routes from another OSPF process or routes from BGP. But it's any redistributed route, basically. Advertised and owned by the originating ASBR, flooded throughout the entire AS, should be a little asterisk there, except for special area types. The advertising router ID is unchanged throughout the AS. That's why the type 4s are needed, by the way, because the advertising router ID is the ASBR's router ID. This internal router in area 20 doesn't have a relationship with that ASBR. Not directly. That's where the type 4s are needed. All right? And that's what they're meaning by this bullet point. Inter-area router LSAs are needed to find the ASBR. Where would those inter-area router LSAs not be needed to find the ASBR? Inside of area 10. Inside of area 10, there are no type 4s. How do we reach the ASBR inside of area 10? Type 1s, right? Remember, the ASBR is advertising type 1s as well. All right. These external LSAs can be summaries. They're not summarized by default, but they can be summaries. All right. So we can actually look to see if we see any type 5s in a router 4. And do we see type 5s? It's interesting that this is the only one outside of type 8 where they actually say type 5. So that's pretty easy to find. And we can see this prefix here. What I'm going to do is actually generate some additional type 5s. Let me go into router 3, show IP interface brief, and I'm going to do, maybe, if I can actually type, interface loopback 1, IP address 1.1.1.1, interface loopback 2, IP address 2.2.2.2, interface loopback 3, IP address 3.3.3.3. And I'm going to go into, if I do show run section router, I'm going to redistribute connected into OSPF. Right now they're doing redistribute static, but I'm going to go into my routing process and I'm going to go into my v4 address family and I'm going to say redistribute connected. Same thing with v6. Well, I didn't do any, I won't do v6. It's the same thing, right, with v6. So now if I go to router 4, I should see those prefixes as well, right? There's the 1, there's the 2, there's the 3. Oops, I kind of inserted some more in there as well. Let me do this. Exit IP access dash list extended or standard. Let's do 1, 2, 3. Oh, I can't give it a name. 1, 2, 3. There. All right. Permit 1.0.0.0. Actually, let's do permit 0.0.0.0, and we'll do 3.255.255.255. And then I'm going to do a route map. 1, 2, 3. Permit 10. Match IP address 1, 2, 3. And then I'm going to go back to my OSPF process. Ah, dang it. Would have been easier just to type it. Router OSPF v3 1. Now address family. Gosh, dang it. Address family IPv4 unicast. Redistribute connected route map 1, 2, 3. And let's do v6. Yeah, I didn't do any v6 prefixes. Basically, I don't want all of these connected routes to be re-advertised. I only want 1, 2, and 3, so I should see that now. It should have filtered them out. I didn't do my access list right. Let me change my access list. I did 3, and I should have done the opposite. The first 3 bits would have been fixed, but let's fix that. So do show run access dash list, show run section access dash list. Yeah, my mask is not correct because I said basically the last 3 bits could be anything. And the first few bits, that should have worked actually, because that should include 1, 2, 3, and 4. If the first 3 bits can be anything, that means the remaining bits have to be 0, which 10 should not be included in that. Oh well, let me do it this way. Just make it simple here. No 10, permit 1.1.1.1, 0.0.0.0, permit 2.2.2, 0.0.0.0, and permit 3.3.3.3. I probably could have just used a prefix list. Show run. Oh, I'm not even in the right router. That's why. I did my redistribution here, but I created my access list on router 1. Ah, you guys should have showed me, told me that. Show run section route map. You just let me troubleshoot? Yeah. Yeah. No route map. It's on the video, but that's okay. Everybody makes mistakes. All right. Yeah, I did. I have to apply the filtering on the router that I'm actually doing the redistribution on. Otherwise, it doesn't do anything. No IP access list. I keep switching back and forth between my tabs, and I'm not paying attention. 1, 2, 3, standard. Oops. So it was, my access list was correct. I just didn't put it in the right place. Do show run section route map. Probably no route map here. Nope. All right. So let's do this again. IP access dash list standard. Let's call this 1, 2, 3. And permit 0.0.0.0, 3.255.255.255. That should permit networks 0, 1, 2, and 3. 0 doesn't exist, but 1, 2, and 3 do. 1.1.1.1, 2.2.2.2, and 3.3.3.3. Route map 1, 2, 3, permit 10. Match IP address 1, 2, 3. And then go into my router OSPF v3. Address family IPv4. Redistribute connected based on route map 1, 2, 3. The route map, which we'll talk about tomorrow, route maps have an, if I do a show run pipe section, I might as well explain what I'm doing here. Access dash list, pipe route map, pipe OSPF v3. What you're seeing here is this is an access list matching those 3 loopbacks. This is a route map which permits, based on wherever I apply the route map. In this case, I'm applying the route map to redistribution, but whatever's permitted by this route map is matching the access list. So it's kind of a double permit. Whatever's permitted by the access list is permitted by the route map. There's an implicit deny at the end of the route map, which means that anything that's not explicitly permitted by the route map would be denied by the route map. And then I'm saying redistributed connected, but only redistribute based on what's permitted by this route map. Make sense? So if I do show OSPF v3 database self-originate, I should see now that I'm only originating 1, 2, and 3. Now, if I go to router 4, I'm only seeing 1, 2, and 3. All right? There's a reason I did that, because I showed you the summary for the type 3s, the area range. We can also do the summary on our ABR, our ASBR for these type 5s. Router 4 just sees them as type 5s, coming in as type 5s. That's the original one that was coming in. That's the redistribute static. These are the redistribute connected for the prefixes that are coming in from those loopbacks I created. But I could summarize these on the originating router, the ABR. I can come in here. I'm already in the address family, right? I'm in the IPv4 address family, and we use summary prefix. And then I specify the IP address and the masks. So in this case, it would be 0.0.0.0/3. All right. Actually, it would not be a /3. It would be a /20 or /6. No, 5. Because it's 1, 2, and 3, which means basically the last 2 bits aren't fixed. Only the first 6 bits of the first octet are fixed. Does that make sense? Because 1 is 0.0.0.0.0.0.0.1, 2 is 0.0.0.0.0.0.10, and 3 is 0.0.0.0.0.0.1. So it's only the last 2 bits that are changing, right? The first 3 bits are fixed. So that would be my summary for those 3 networks. Now, if I go back to router 4, I'm going to now see that summary, but it didn't work. What am I doing wrong with my math? It put the summary, there it is. Okay, so it did work, yeah. Starting to question myself now that I'm messing up on all these other configurations, but you get why that's the summary for 1, 2, and 3. If you don't, that's okay, but yeah, we're summarizing those 3 loopbacks. The point is, you can summarize on an ABR, you can summarize on an ASBR, but from router 4's perspective, it's just a type 5 LSA. Again, router 4 doesn't know that it's actually a summary. It just is an external network. All right? So going back to the book here, we only had the one external network, which was the 16. I've now created an additional one. And if I was to drill down, you would see pretty much what you would expect to see for those prefixes. You would see the advertising router, which is the ASBR. Again, from router 4's perspective, I have no relationship with this router, but I am getting the type 4s. And the type 4s allow me to identify which ABR to go to get to the ASBR, and then I use my type 1s to figure out how to get to the ABR. All right? Also notice that the prefix address, in this case, that's just the network that's being advertised. Here is the 10 network, here is the 0 network. This is the prefix length. This is the actual metric type. Now, this has nothing to do with LSA type. This has to do with how the metric is treated as you're moving through the OSPF domain. I'll mention it briefly. We're going to see this again later on. But if you insert a route as type 2, the cost, the seed metric for redistributed routes in OSPF is 20. Unless you're redistributing from BGP, the seed metric for all OSPF routes that are all routes that are redistributed into OSPF is 20. Okay? Now, because I built this route map, I can actually come in, make sure I'm in the right router this time. I can actually come in, and if I do a show run pipe section router, I can actually modify how that redistribution takes place by modifying the route map. This is one of the benefits of actually creating a route map, is now I can do set metric. I can set the seed metric for those prefixes that I'm redistributing, and I can also set the metric type to 1. External 1. Oh, come on. Type external. Set the metric type. Type 1. There we go. All right. ISIS uses external and internal. Okay. So if I go back to router 4 now, and you look at this, we can now see it's coming in as a type 1. The seed metric is 200. But what does that mean from the overall metric for the route? If I do a show IP route, look what happened with the type 2. The seed metric never changed. So when you insert an external route as a type 2, the initial seed metric, which by default is 20, doesn't change no matter where you go in the autonomous system. If you insert it as a type 1, that initial seed metric, which was 200, now gets incremented with the cost of the links along the path to the ASBR. That's the difference between type 1 and type 2. Whether the metric increments or whether the metric doesn't increment. Doesn't matter in this particular case. We don't use this metric to figure out how to get to those external networks. We use other type LSA types to learn how to get to the ASBR. So that initial seed metric is kind of irrelevant for those external networks because I don't really use that metric to figure out how to reach that destination. If I was to drill down into that route, show IP route, show IP route, let me do my 16 here. No, let me see. Show IP, OSPF, show IP route, OSPF V3, 10.0.0.0. Dang it, I can't do that? All right, let's try this. Show IP route. I should be able to see the details. I don't know why it's doing that. Probably because I'm running OSPF V3, but yeah, it's weird. I should be able to see the overall metric. No, I can't do that. Show IP route OSPF 10.0.0.0. No, that's not going to work. If I was running traditional OSPF, I should be able to see that detail. But anyway, I'll show you that a little bit later on. There's a way that you can kind of drill down into the routes and see what the overall metric is. But again, that 20 in this particular case doesn't really matter. Why doesn't it matter? Because there's only one router generating this external prefix. And I don't use this 20 to figure out how to get to that ASBR. I use other LSA types to figure out how to get to the ASBR. Type 4s, type 1s, type 2s, and so on. Not type 2s, but type 1s, type 9s, type 4s. And it's the metrics for those LSAs that allow me to define what the overall path metric is to reach that external network. This just happens, the type 1 just happens to reflect that total path cost. I would typically change my external routes to type 1 if I have more than one ASBR that's generating that same external prefix. So I can make sure I'm choosing the best path to get to that external network. Does that make sense? All right. Let's see here. We're doing a lot more than what they're doing here in the lab, but link states. We're almost done. We only have really two more to talk about. Link states are which type? Oops, it was on the screen there. Link states are which types? Which types? Which types are they? They're type 8, obviously. See, 8, 8, 8, 8. 8s represent what? They are type 7s, yes. Yeah. No, they're type 18s. No. They're type 8s, which are link local. Okay? So this would normally be exclusive to IPv6 if I was running classic OSPF v3 and classic OSPF v2. Or if I was just running classic OSPF v2, I wouldn't see type 8s. If I was running classic OSPF v3, I of course would see type 8s because that's v6. But because we're running OSPF v3, we're also going to see type 8s. All right? Very simple LSA type in this particular case because it really just describes link local information. But what's important to understand about the type 8s is what is really the scope of a type 8? what would you think the scope of a type 8 would be? It does say that type 8s are propagated throughout the entire autonomous system, right? We saw that in the diagram. These are inter-area LSAs. They move from one area to the next. But look at the arrows. They don't actually move from one area to the next. They are link local. This ABR over here could care less what the link local addresses are here, because this router can never get to those link local addresses. Remember, link local addresses are not routable. So you're only going to share type 8 LSAs with other routers that you're in a common subnet with. So they're not even inter-area or intra-area. They're link local. All right? They're literally LSAs that you're only exchanging with your peers. And obviously if we're going to look at these, we're going to go ahead and type link. Those are my link states. And you'll see here, actually, let me scroll down here. You'll see the link that's represented between the different peers, right? Now you would expect with these type 8 LSAs to see link local information, like FE80 addresses. But again, the scope is really, it describes the link, but it doesn't describe the link in the terms of the FE80 prefix, right? So this is the link local address for this router on that link. That's router 1. This is the link local address for which is basically the v4 address. Now, if I was to look at this from a v6 perspective, it would look different because that's v4. If you look at this from a v6 perspective, you do see the link local addresses. There is no concept of link local in v4. All right? So this is the prefix. This is the subnet, but this is how I represent myself with a link local address in IPv6 for that particular broadcast domain. So it's kind of strange that you would see these with v4 because we really didn't have a concept of link local in v4. 14.1 is a routable address. We can get to that network from anywhere because the 14 subnet is being advertised throughout the autonomous system. So really the type 8s are more important when you're talking about v6 than when you're talking about v4, but they are represented in v4 as well. All right. The link LSAs on router 4 describe the neighbors that are both connected to the Ethernet 1.0 prefix of 14.0. The link LSA shows that only one IPv4 prefix is associated to the link, which, by the way, would be the case for v4 anyway, right? All right. So that is it for that discovery. We'll go ahead and wrap that up. We're going to talk about more details in our next section about how we manage the database, how we can identify the changes in the database, the link state ages, that kind of thing. And then we'll get into some special area types a little bit later on.
Now, when we talked about OSPF in the beginning, we talked about how OSPF is a incremental protocol, meaning that it sends out routing updates when there are changes to the topology. And traditionally, that's what link state routing protocols do. And they're very efficient in that regard. But in the case of OSPF, we have something called a paranoid update. Every 30 minutes, OSPF is going to flood its LSAs throughout the entire area and ultimately throughout the entire OSPF autonomous system. If you look at the database output here, we can see that there are two fields, the age and the sequence number. Okay, and these are very, very important fields to identify when you're analyzing the database. The sequence number is a relatively simple concept to understand. It starts at 0001. I'm not going to write the whole number out. And then each time there is an update to that particular LSA, that number is going to increment. So this particular one has had 29 different updates. Now that doesn't mean that the network has changed 29 times. It simply means that either the age timer reached its 30 minutes and we did a flood, or in fact there was some sort of change to that linked state information. Each update or regenerated LSA in this case is going to result in that sequence number being incremented. That age variable, that one that you see on the left there, the router link state age, 405 for the first one, 902 for the second one, 405 for the third one, that is an incremental timer. If a network change occurs, we're going to generate an updated LSA by incrementing the particular sequence number, and then we are going to reset the age for that particular LSA. Now, if that LSA reaches that age variable of 30 minutes, meaning that we haven't created any updates in that LSA in the last half hour, we're going to go ahead and regenerate those LSAs, and then we're going to increase our sequence number, which is going to get flooded throughout the OSPF autonomous system. So when you run the command show IP OSPF database, you're going to see the value of the link state aging timer for all of the LSAs. Now this last statement here is kind of interesting because it states here that you will not see the age variable higher than 1800 seconds, but in actuality, I have seen the value higher than this. I'm not sure exactly why that is the case, but there are instances where I've seen the value higher than 1800 seconds. But in any regard, the OSPF paranoid update time is 30 minutes. Okay? All right. Now let's talk a little bit about this process of how we synchronize the database. In EIGRP, when we talk about EIGRP, it's pretty much our neighbors are down or our neighbors are up. And once we're fully adjacent, we simply exchange our routing information. But in the case of OSPF, we go through a sequence of events to establish our full adjacency. And what I'm going to do is I'm going to break down each of these steps here and talk about what is happening in this process. So we start in the down state. And in the down state, we've essentially configured OSPF, maybe, but we haven't actually generated any hello packets. So you probably won't be in this down state for very long, right? Because you're typically going to generate a hello packet within a few seconds. As soon as I generate a hello packet, I'm going to move to the init state. And in the init state, we have sent a hello. We're generating a hello based on our OSPF configuration, which includes our router ID and all of the other parameters of our OSPF configuration. But I have not yet received a hello. Okay, particularly, I haven't received a hello where my router ID is listed in my neighbor's hello packet in the neighbor list. When we go through the discovery, we'll take a look at some of the Wireshark captures, but inside of the hello packet, there is a field called the neighbor list or the neighbor field, where I will see a list of all of the neighbors that that the router generating that hello packet recognizes. Now, assuming that my neighbor receives my hello packet and my neighbor identifies that I have the appropriate parameters available or I have the appropriate configuration available to be able to form an adjacency with that peer, that router will add my router ID to their neighbor list. And in turn, I will add their router ID to my neighbor list. So when we're generating our hello packets, we're going to see each other in our neighbor list. And this is when we move into a two-way state. Routers that are said to be in a two-way state recognize each other, and they recognize that the parameters are appropriate and they have the appropriate settings to actually move on to synchronizing the databases and ultimately forming a full adjacency. Now, the next step that takes place is that we are going to negotiate who is going to be responsible for initiating the exchange of routing information. And in some cases, we're going to take a look at who is going to be elected as a designated router for a particular multi-access network, and who's going to be elected as a backup designated router. In this process, this is called the Xstart state, we are going to be exchanging something called database descriptor packets. And the database descriptor packet, quite simply, simply stated, at least in this diagram, is, hey, here's my router ID. I would like to start the exchange of link state routing information, and please let me know if you're ready to go. This router, in turn, will send its own Xstart packet saying, no, this is my router ID. I actually happen to have a higher router ID. So I will be responsible for initiating this exchange of information. It's a little bit more complicated than that, but quite frankly, it's not really necessary at this point to kind of go into the details. But in this particular case, we're not really exchanging any actual routing information or link state information. We're simply negotiating who's going to be responsible for initiating the exchange, who's going to be the master, who's going to be the slave, who's going to be the designated router, who's going to be the backup designated router, and so on. Okay? Now, a couple of points here in the text. We're sending these hello packets to 224.0.0.5, which is the all OSPF routers multicast address for IPv4. And again, after adding the peer or the neighbor to our list, we're going to move or transition from the init state to the two-way state based on what we see in the hello packet. And that is the two-way state adjacency. Again, if it is a broadcast network, we're going to do our DR/BDR election, meaning we're going to elect the chief for that multi-access network so that we can manage the adjacencies and manage the exchange of link state information, and then we'll elect a backup as well in case the DR is no longer available. So that master-slave relationship gets determined between the routers that are communicating. It is possible that we may get stuck in this particular state if there's an MTU mismatch, for example, between the peers. OSPF doesn't really like to have an MTU mismatch, although we can override that behavior and force the adjacency to occur even with an MTU mismatch with a special command. The idea is that these link state databases can get rather large, and if we're encapsulating a lot of information and there's an MTU mismatch, it's entirely possible that we may run into a situation where packets are being fragmented, and because of those packet fragmentations, there may be some erroneous errors or issues with the synchronization. So by default, OSPF requires that you have a matched MTU for adjacencies to form. Otherwise, you'll continue to stay in that Xstart state and you won't move beyond to the exchange state. All right, now assuming that we are able to move beyond the exchange or Xstart state, we will now move into the exchange state. Unlike the name or what the name implies, the exchange state is not actually where we are exchanging link state information. OSPF is a rather robust protocol, and the link state databases can get rather large. So as a point of efficiency, the IETF decided that rather than exchange our entire routing database, rather than exchanging the entire link state database, we are going to go ahead and exchange, again, via a database descriptor packet, a summary of my link state database. So if router 1 already has, thousands of entries in its database, or 2 has thousands of entries in its database, it's entirely possible that those entries have some redundancies, or at least the same information. So by exchanging these essentially summaries of the database, router 1 and router 2 can only request the exchange of information that they don't have. So if there's some common entries in each of the databases, we're not going to waste time exchanging that information because we both already have that information. So in essence, this exchange state allows us to kind of summarize not only what our databases include, they'll look at sequence numbers to identify whether or not maybe one of the routers has maybe newer information than the other router. And then finally, well, not finally, but the penultimate step would be that we go into the loading state. And this is where we're actually exchanging the details of the link state information. So this router 1 says, oh, okay, I see you have something in your database that I don't have. I'm going to go ahead and send you a link state request saying, can you provide me the complete details of this information? That will be followed up with a link state update, and then we'll finally send our link state acknowledgement. And this will happen in both directions until the databases are completely synchronized. Once these databases are completely synchronized, the routers are said to be in a full state. All this being said, from down to init to two-way to exstart to exchange to loading to full, there are two states that are non-transitionary states in this particular process. Certainly the full state, that's kind of the final endpoint that we're trying to reach, right? Being a fully adjacent. But then we have the two-way state. Some routers will maintain their status with other peers in two-way. This occurs when you have a multi-access network, you have a DR and a BDR. Those DRs and BDRs are going to form a full adjacency with all the other routers in that broadcast domain. But then the routers that are neither a DR or a BDR, what we call a DR other, they're going to only maintain a two-way adjacency with the other DRs in that multi-access network. So they recognize that they exist, they understand they exist, they show up on their neighbor list, but they don't move beyond the two-way state because there's no need to form that full adjacency with those routers in that broadcast domain because we're establishing those adjacencies with our DR and BDR. All right, so the text here is just kind of describing what we just went through, and that's the process. Later on, we'll actually take a look at that process in our discovery by doing a debug IP OSPF events and looking at the packets and looking at the process of moving through those particular states. Okay? We've talked about this particular concept a couple of different times in a multi-access network. Any multi-access network is essentially a network where you can have multiple hosts participating within the same broadcast domain. In a multi-access network, we elect a DR, and it's the responsibility of that DR to propagate LS information or link state information to the other members of that multi-access domain. So if a link goes down over here, router 4 is going to notify the DR of that link information or that link state change in the form of a link state update. The DR then is going to be responsible for propagating that information to the other routers, in this case the DR other, which is neither a DR or BDR. And if I had other ones in that segment as well, those routers would be receiving that information as well. All right, so it's just a way for us to essentially create a more efficient way of exchanging information. The DR is essentially the chief. The DR is responsible for managing that broadcast domain. It's not within the area. It's not within the autonomous system. The reality is that you can have multiple DRs within an area. You can have multiple DRs within an autonomous system. It just depends on how many multi-access networks you have. Additionally, are all routers or all OSPF routers multicast address is 224.0.0.5 or FF02:5, but our DR/BDR multicast address is 224.0.0.6 or FF02:6. Okay? All right, the last thing we'll talk about here is the execution of the SPF algorithm. This only occurs if there's a change in the topology, meaning that we have new links or we lost some links, and we need to figure out whether or not we have to recalculate our shortest path tree, right? Our shortest path first tree. So only changes in the actual topology will require an SPF execution. So the paranoid update, for example, is not going to trigger an SPF execution because the link state information is not actually changing. We're just resynchronizing that information as part of the process. Okay? We can see how many times the SPF algorithm has been executed by using the show OSPF v3 or show IP OSPF command. In this case, we're adding the IPv4 keyword to see in the this output in regards to IPv4. We can see that the SPF algorithm has been executed 6 times. If this number continues to increase, that could be an indication that there's some instability within the OSPF area, and you may have to kind of evaluate what's going on in that area and why the SPF algorithm is constantly being executed. We don't want that to occur because that takes processing time and CPU cycles, but it also means that there's probably something wrong with the network itself, or at least it could be an indication of that. All right. By the way, when you are exchanging type 3 LSAs, right, inter-area changes, and this is a very important concept, that does not trigger an SPF recalculation if the best path calculation stays the same. And that's a really important concept to understand. Because type 3 LSAs are summaries, it is possible that maybe a prefix within that summary goes down, so maybe the metrics for the summary might change. That's not going to necessarily trigger an SPF recalculation. If we lose a summary, that certainly could, but not if some basic elements of the summary change. Okay? All right. So we're going to wrap up this section here. We've completed kind of our introductory section to OSPF. In the next module, we're going to take a look at how we can optimize OSPF, in terms of using things like summarization, special area types, and so on. And then we'll continue on beyond that to talk about things like authentication. So we'll see you guys in the next module.